Good evening, and welcome to The Gentle Scientist. Tonight, we drift beyond Earth into the quiet vastness of space, where worlds of fire and ice circle our sun in an ancient dance that began before life itself. Our solar system is a family of worlds, each with its own character, its own history, written in stone and ice and swirling clouds. Some are giants that could swallow Earth whole. Others are small and cold, drifting at the edge of darkness. Together, they form a neighborhood bound by gravity and light, shaped by the same ancient materials that built the stars themselves. Tonight, we will visit them all, one by one, beginning with the sun that holds everything in its embrace, and journeying outward through the rocky inner planets, past the asteroid belt where fragments of creation still drift, into the realm of giants with their storms and moons, and finally to the frozen frontier where comets sleep in the darkness. Each world we encounter will reveal something unexpected, something that challenges what we thought we knew about how planets form and evolve. If you find comfort in these quiet journeys through science and space, I invite you to subscribe to The Gentle Scientist. Let me know in the comments where you are watching from, what time it is there, or simply share any thoughts that drift through your mind as you listen. For now, settle in. Let your breathing slow. Let the weight of the day lift away. We begin our journey at the heart of everything, where a star burns with the light of 1 billion years, where nuclear fusion turns hydrogen into helium and releases the energy that makes all life possible. The sun awaits, and beyond it, worlds beyond counting. Let us drift there together, gently, into the welcoming darkness where planets turn and time moves slowly. If you have ever stood outside on a clear morning and felt the gentle warmth spreading across your skin, you have felt the touch of something truly ancient and magnificent. That warmth has traveled a long way to reach you. About 93 million miles, in fact. And it has done so at the fastest speed anything in the universe can travel, the speed of light. Yet even at that extraordinary pace, it takes sunlight a little more than 8 minutes to cross the vast emptiness between the sun and the earth. When you watch a sunrise, you are not seeing the sun as it is in that exact moment. You are seeing it as it was 8 minutes ago. In a way, every glance at the sun is a small act of time travel, a glimpse into the recent past. But the story of that light stretches back much further still. The photons that warm your face on a summer afternoon were not born at the sun's surface. They were born deep within its core, in a furnace so dense, so impossibly hot, that atoms themselves are stripped apart and reformed into something new. And before those photons could escape into space, they had to wander through the sun's interior for tens of thousands of years, perhaps even hundreds of thousands, bouncing and scattering in a long, slow journey outward. By the time sunlight finally breaks free of the sun and races toward Earth in just over 8 minutes, it has already been traveling, in a sense, since before the pyramids were built, since before humans walked the Earth at all. The sun is, quite simply, enormous. It is so large that it defies easy imagination. If you could hollow it out like a great golden bowl, you could pour more than 1 million Earths inside and still have room to spare. Its diameter stretches about 865,000 miles, roughly 109 times the width of our own planet. If Earth were the size of a small pebble, the sun would be a giant beach ball, towering beside it. And yet, for all its grandeur, the sun is just an ordinary star, a middle-aged, medium-sized yellow dwarf, glowing steadily in a galaxy filled with hundreds of billions of other stars. Some are far larger, some are far smaller. But this one is ours, and without it, we would not exist. The sun accounts for more than 99% of all the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids and comets and dust, together make up less than 1%. The sun's gravity is what holds our cosmic neighborhood together, keeping Earth and all her siblings in their graceful orbits, preventing us from drifting off into the endless dark between the stars. To understand how the sun works, we must travel inward, through layers of fire and light, to the place where its power is born. At the very heart of the sun lies the core, a region of almost unimaginable density and heat. Here, temperatures reach about 27 million degrees Fahrenheit, and the pressure is so intense that it would crush anything we know into oblivion. In this extreme environment, something remarkable happens. Hydrogen atoms, the simplest and most abundant element in the universe, are forced together so tightly that they fuse into helium. This process is called nuclear fusion. It is the same reaction that powers hydrogen bombs, but in the sun, it happens continuously, peacefully, and on a scale beyond comprehension. Every single second, the sun converts about 620 million metric tons of hydrogen into helium. In that same second, roughly 4 million metric tons of matter are transformed directly into energy, released as light and heat that will eventually warm planets and moons across the solar system. This is the engine that drives our star. This is the alchemy that turns simple atoms into the warmth that makes life possible. But the energy born in the core cannot simply leap outward. It must travel through the sun's many layers, each one presenting its own challenges. Just outside the core lies the radiative zone, a thick shell where energy moves outward in the form of radiation, bouncing from particle to particle in a slow, wandering path. The plasma here is so dense that a photon may take hundreds of thousands of years to make its way through this region. Imagine a single ray of light struggling through a crowd so thick it can barely move, inching forward over millennia. That is the radiative zone. Above this lies the convective zone, where the sun's material behaves more like a boiling pot of water. Great currents of hot plasma rise toward the surface, release their heat, and then sink back down to be warmed again. This churning motion creates a pattern on the sun's visible surface called granulation, a patchwork of bright cells surrounded by darker edges, each one about the size of a small country on Earth, constantly shifting and renewing. The surface we see when we look at the sun, the glowing face that lights our days, is called the photosphere. It is not truly a solid surface, for the sun has no solid ground, but rather the outermost layer from which light escapes into space. The photosphere has a temperature of about 10,000 degrees Fahrenheit, which sounds impossibly hot, but is actually much cooler than the layers above and far cooler than the core. It is from here that sunlight begins its 8-minute journey to Earth. Above the photosphere lies the chromosphere, a thin reddish layer visible during total solar eclipses. And above that, the corona, the sun's outermost atmosphere. The corona is a ghostly halo of superheated plasma that extends millions of miles into space. Strangely, it is far hotter than the surface below, reaching temperatures of several million degrees. Scientists are still unraveling the mystery of why the corona is so hot, but it is here that the solar wind is born. The solar wind is a constant stream of charged particles, mostly electrons and protons, flowing outward from the sun at speeds of up to 2 million miles per hour. This invisible river of particles fills the space between the planets, creating a vast bubble called the heliosphere that stretches far beyond the orbit of Pluto, perhaps 3 times as far. Within this bubble, we are still under the sun's influence. Beyond it lies interstellar space, the realm between the stars. Sometimes, the sun grows restless. Dark patches called sunspots appear on its surface, regions where intense magnetic fields have cooled the plasma below. Sunspots can be enormous, sometimes larger than Earth itself. They tend to appear in cycles, rising and falling over roughly 11 years. When sunspot activity is high, the sun becomes more volatile, more prone to sudden outbursts of energy. These outbursts include solar flares, tremendous explosions of radiation that can release energy equivalent to billions of nuclear bombs in just a few minutes. Even more dramatic are coronal mass ejections, great eruptions of plasma and magnetic field hurled outward into space. When these reach Earth, they can compress our planet's magnetic field, trigger beautiful auroras near the poles, and sometimes disrupt satellites, power grids, and communications. The sun, for all its life-giving warmth, is also a reminder that we live beside a star of immense and sometimes unpredictable power. Yet the sun is not eternal. It is about 4.5 billion years old, roughly halfway through its expected lifespan. For another 5 billion years or so, it will continue to burn steadily, fusing hydrogen into helium in its core. But eventually, the fuel will begin to run low. The core will contract and heat up. The outer layers will expand. The sun will swell into a red giant, growing so large that it may swallow Mercury and Venus, and perhaps even scorch the Earth to a cinder. But that is a story for a distant future, so far away that it belongs more to the realm of dreams than to our waking lives. For now, the sun rises each morning as it has for billions of years, faithful and warm, painting the sky in shades of gold and pink. For now, it is our steady companion, the anchor of our days, the source of every green leaf and flowing river and beating heart. Long before we understood the science of fusion and plasma and electromagnetic radiation, humans looked up at the sun with wonder. Ancient Egyptians worshipped Ra, the falcon-headed god who sailed across the sky in a golden boat, bringing light to the world each day. The Greeks honored Helios, who drove a blazing chariot, pulled by fiery horses from dawn to dusk. In cultures around the world, from the Aztecs of Mesoamerica to the Shinto traditions of Japan, the sun has been revered as a deity, a source of life, and a symbol of divine power. Perhaps they understood something essential, those ancient peoples. Not the physics, but the poetry. The sun is not merely a ball of burning gas. It is the reason we exist at all. Every beam of light that reaches Earth carries with it the story of atoms transformed, of energy released, of a star pouring itself out across the darkness so that distant worlds might be warm. The sun's light travels outward in all directions, racing through the void at speeds beyond imagination. And the first world to catch its warmth is a small messenger named Mercury. This tiny planet, smallest of the 8 that circle the sun, moves through space with a swiftness that earned it the name of the Roman god who carried messages between worlds. Mercury is a world of extremes, a place where the sun looms 3 times larger in the sky than it does from Earth. If you could stand on its surface, you would see our star as a monstrous golden orb overwhelming the black expanse of space. The heat there is fierce beyond measure. During the long Mercurian day, temperatures soar to 430 degrees Celsius, hot enough to melt lead, hot enough to vaporize zinc. The rocks themselves seem to shimmer in that relentless light, baked by radiation that never softens, never pauses. Yet Mercury holds a paradox within its extremes. When night finally falls, when the sun sinks below the horizon and darkness claims half the planet, the temperature plummets. With no atmosphere to trap the day's warmth, the heat escapes into space as quickly as breath on a winter morning. By dawn, before the sun returns, the surface can drop to minus 180 degrees Celsius. Few worlds in our solar system experience such dramatic swings, such violence of temperature compressed into a single cycle of light and dark. A year on Mercury passes quickly. The planet races around the sun in just 88 Earth days, moving faster than any other world in our solar family. Its orbit is a tight ellipse, swinging close to the sun, and then retreating slightly, tracing the same path again and again with mechanical precision. Ancient astronomers noticed this swiftness and named the planet for Mercury, the fleet-footed messenger who wore winged sandals and carried words between gods and mortals. But here is where Mercury reveals its strangest secret. Though its year is brief, its day is astonishingly long. A single rotation of Mercury on its axis takes 59 Earth days. The mathematics of this creates something almost surreal. Because of the interplay between its rotation and its orbit, one complete day-night cycle on Mercury, from sunrise to sunrise, lasts 176 Earth days. 2. Mercurian years pass in the time it takes the sun to cross the sky once, set, and rise again. If you stood in one place and watched, the sun would creep across the heavens with agonizing slowness, pausing, even appearing to move backward briefly before continuing its journey. Time itself seems to hesitate on this strange, scorched world. The surface of Mercury bears the scars of billions of years. When spacecraft finally reach this innermost planet, when cameras turned their lenses toward its cratered face, they revealed a landscape that looked hauntingly familiar. Mercury resembles our own moon, its surface pocked and battered by countless impacts from asteroids and comets that rained down during the solar system's violent youth. These craters overlap and crowd together, some ancient and worn smooth by the passage of eons, others sharp and fresh, their rays of ejected material still bright against the darker plains. Among these countless scars, one stands out. The Caloris Basin stretches 1,550 kilometers across, one of the largest impact craters in the entire solar system. The collision that created it was so violent that it sent shockwaves through the entire planet. On the opposite side of Mercury, directly across from Caloris, the ground buckled and fractured into chaotic, jumbled terrain. The planet rang like a bell, and the evidence of that ancient catastrophe remains frozen in stone, a permanent record of a day when fire and destruction reshaped an entire world in moments. Beneath its battered surface, Mercury hides another mystery. For such a small planet, it is surprisingly dense, surprisingly heavy. Scientists studying its gravity realized that Mercury must have an enormous iron core, far larger in proportion to its size than Earth's core. This metallic heart makes up about 85% of the planet's radius. If you could somehow peel away Mercury's rocky outer shell, you would find a sphere of iron nearly as wide as the entire planet, glowing with residual heat from its formation. Why Mercury should have such a disproportionately large core remains a puzzle. Perhaps a massive impact early in its history stripped away much of its rocky mantle, leaving the dense metallic core exposed. Or perhaps it formed in a region of the solar nebula where iron was more abundant, where the building blocks of planets were richer in metal. Either way, this iron heart generates something unexpected. Mercury has a magnetic field, weak compared to Earth's, but present nonetheless. Deep within that core, liquid iron still flows in slow currents, creating invisible lines of magnetic force that extend into space, deflecting some of the solar wind that constantly streams outward from the sun. And here is perhaps the most surprising discovery of all. Despite being the closest planet to the sun, despite enduring temperatures that would melt metal, Mercury has ice. In the permanently shadowed craters near its poles, where sunlight never reaches, where the walls are high enough to block even the scattered glow of the horizon, temperatures remain cold enough for water ice to survive. Radar observations detected it first, bright reflections from the darkness. When the Messenger spacecraft arrived, its instruments confirmed what seemed impossible. Tucked away in eternal shadow, protected from the sun's fury by mere geometry and chance, ice has persisted for perhaps billions of years. Some of these frozen deposits may even be covered by a dark layer of organic compounds, complex carbon-based molecules delivered by ancient comets. Humanity's exploration of Mercury has been challenging. The planet's proximity to the sun makes it difficult to reach. Spacecraft must shed enormous amounts of orbital energy to slow down enough to enter Mercury's orbit, and once there, they must endure intense heat and radiation. Only 3 missions have ever visited this small world. Mariner 10 flew past 3 times in the 1970s, capturing the first close-up images, and revealing roughly half the planet's surface. Decades passed before Messenger arrived, becoming the first spacecraft to orbit Mercury in 2011. For 4 years, it circled, mapping every crater, measuring the magnetic field, analyzing the surface composition, and confirming the presence of ice in those shadowed polar regions. Now, Bepi Colombo is on its way, a joint mission between Europe and Japan, flying through space on a complex trajectory that will take 7 years to reach Mercury. When it arrives, it will split into 2 separate orbiters, one studying the surface and interior, the other measuring the magnetosphere and the environment around the planet. Together, they will answer questions that Messenger could not, peering deeper into Mercury's mysteries, reading the history written in its ancient battered crust. Standing on Mercury would feel alien in ways difficult to imagine. The gravity is only about 1/3 of Earth's, so you would feel light, almost buoyant. The sky would be black even at noon, for there is no atmosphere to scatter light into blue. Only the thinnest wisp of an exosphere exists. Atoms of sodium, potassium, and oxygen torn from the surface by the solar wind and solar radiation. So tenuous, it is essentially vacuum. You could see stars at midday if you looked away from the sun's overwhelming glare. And that sun itself would dominate everything. A furious golden disk that never blinks, never softens, pouring heat and light onto stone that has known nothing else for 4.5 billion years. Moving outward from the sun's blazing embrace, we arrive at a world shrouded in mystery, a planet that glows so brilliantly in Earth's sky that ancient peoples called it the morning star and the evening star, never realizing they were seeing the same world at different times. Venus hangs there in the twilight, luminous and serene, the brightest planet visible from Earth. Its beauty is deceptive, a veil that hides one of the most hostile environments in the solar system. Venus is Earth's twin in size, almost identical in diameter and mass. If you place the 2 planets side by side, they would appear remarkably similar. 2 rocky worlds formed from the same ancient cloud of dust and gas. Yet beneath that surface resemblance lies a profound divergence, a story of 2 planets that began so much alike and became so utterly different. Where Earth bloomed with oceans and life, Venus descended into an inferno from which it has never escaped. The first hint of Venus's strangeness comes from its thick atmosphere, a crushing blanket of carbon dioxide that weighs down on the surface with a pressure 90 times greater than Earth's. To stand on Venus would be like diving a kilometer beneath Earth's oceans, the air pressing against you from all sides with relentless force. But the atmosphere offers no oxygen, no relief. Only carbon dioxide laced with clouds of sulfuric acid that drift through the upper layers in thick yellowish bands. These clouds reflect sunlight with such brilliance that Venus outshines every other planet in our sky. They also trap heat with devastating efficiency. The greenhouse effect on Venus has run wild, spiraling beyond any possibility of recovery. Sunlight filters through the clouds and warms the surface, but the thick carbon dioxide atmosphere prevents that heat from escaping back into space. Temperature builds upon temperature, trapped and recycled, until the surface reaches 465 degrees Celsius. This is hotter than Mercury, despite Venus being nearly twice as far from the Sun. The heat is so intense and so evenly distributed that it varies little between day and night, between equator and poles. The entire planet bakes in an oven of its own making, a furnace that never cools, never rests. Above this hellish surface, the clouds themselves hold their own mysteries. They circle the planet in just 4 Earth days, racing around Venus in super-rotating winds, while the planet itself turns slowly beneath them. These winds reach speeds of 360 kilometers per hour in the upper atmosphere, howling storms that dwarf the fiercest hurricanes on Earth. Yet near the surface, the air barely moves. The thick atmosphere and high pressure create a strange, sluggish environment where the wind is more like a slow, heavy current than the familiar breezes we know. Venus rotates on its axis in the opposite direction from most other planets, a retrograde motion that remains one of its greatest puzzles. While Earth and most of its siblings spin counterclockwise when viewed from above the Sun's North Pole, Venus turns clockwise. The Sun rises in the west and sets in the east, though you would never see it through the perpetual clouds. Even more remarkably, Venus rotates so slowly that one day on the planet, one complete turn on its axis, takes 243 Earth days. Its year, the time to orbit the Sun, lasts only 225 Earth days. A day on Venus is longer than its year. The mathematics of this creates a solar day, from sunrise to sunrise, of about 117 Earth days. Time moves differently here, stretched and inverted, as if the planet exists slightly out of sync with the rest of the solar system. Why Venus should rotate backward and so slowly remains uncertain. Perhaps a massive collision early in its history struck with just the right angle and forced to reverse its spin. Or perhaps gravitational interactions with the Sun and its thick atmosphere gradually slowed and then reversed its rotation over billions of years. The planet offers no easy answers, keeping its secrets locked beneath clouds that have hidden its surface since before humans first looked up at the stars. When scientists finally pierced those clouds with radar, when spacecraft descended through the acid haze to glimpse the landscape below, they revealed a world dominated by volcanism. About 80% of Venus's surface is covered by smooth volcanic plains, vast sheets of solidified lava that stretch across hemispheres. Towering volcanoes rise above these plains, some of them enormous. Mont Mons reaches 8 kilometers high, its slopes built from countless eruptions over millions of years. Maxwell Montes, Venus's highest mountain range, climbs even higher, its peaks rising 11 kilometers above the average surface. The question of whether Venus remains volcanically active today lingers in the minds of planetary scientists. Some evidence suggests that volcanic activity may have occurred in the geologically recent past, perhaps within the last few million years, or even more recently. Certain regions show features that look fresh, unweathered by the slow chemical reactions that alter rock in Venus's corrosive atmosphere. The European Venus Express mission detected variations in sulfur dioxide levels in the atmosphere that could indicate ongoing eruptions. Lightning detected in the clouds might be linked to volcanic plumes injecting particles into the air, yet conclusive proof remains elusive, hidden beneath the veil of clouds that never parts. Perhaps the most tantalizing question about Venus concerns its distant past. Could this scorched, poisonous world have once been more like Earth? Computer models suggest that billions of years ago, when the sun was slightly cooler, Venus might have had liquid water on its surface. Oceans could have existed, perhaps for as long as 2 billion years, a time span longer than it took for life to arise on Earth. If Venus once had oceans, what happened to them? The answer lies in a runaway greenhouse effect that began slowly and then accelerated beyond control. As the young sun gradually brightened, Venus received more heat. Water began to evaporate. Water vapor itself is a greenhouse gas, trapping more heat, causing more evaporation. The cycle fed on itself, a feedback loop with no natural break. Eventually, all the water evaporated into the atmosphere. At those high temperatures, ultraviolet light from the sun split water molecules apart into hydrogen and oxygen. The light hydrogen escaped into space, lost forever, while the oxygen reacted with rocks on the surface. Venus lost its oceans one molecule at a time, a slow catastrophe that transformed a potentially habitable world into the furnace we see today. This history makes Venus a cautionary tale, a warning written in planetary atmospheres about the fragility of climate. Scientists study Venus not just out of curiosity, but to understand how greenhouse effects work, how planets respond to increasing temperatures, how worlds can cross thresholds from which there is no return. What happened on Venus serves as a distant mirror, showing what can occur when atmospheric carbon dioxide rises too high, when heat begins to trap more heat, when a planet's climate spirals beyond the reach of its own corrective mechanisms. Only a few spacecraft have successfully landed on Venus's surface, and all of them were Soviet. The Venera program, a series of missions launched during the 1970s and early 1980s, achieved what seemed impossible. Venera 7 became the first spacecraft to transmit data from another planet's surface in 1970, surviving for 23 minutes before the heat and pressure overwhelmed its systems. Later missions improved, building more robust landers that could withstand the conditions for longer. Venera 13 lasted a remarkable 127 minutes, long enough to capture color photographs of the rocky, orange-tinged landscape and to analyze the composition of the soil. Those images revealed a world of flat, rocky plains strewn with sharp-edged stones, lit by the dim, orange glow that filters through the thick clouds. The light is strange, diffuse, scattered by the dense atmosphere until it seems to come from everywhere and nowhere. The sky appears orange-yellow, heavy with haze. The photographs are grainy, distorted by the hostile environment, yet they remain some of the most remarkable images ever captured. To see the surface of Venus through the eyes of those brief mechanical visitors is to glimpse a world utterly alien, utterly inhospitable, yet undeniably real. No human will ever stand on Venus. The heat would kill in seconds. The pressure would crush. The atmosphere would corrode and dissolve. Even our most advanced robots struggle to survive more than a few hours. Yet Venus continues to fascinate precisely because it is so extreme, so different from Earth, despite their similarities in size and composition. It challenges engineers to design better instruments, better materials, better ways to explore environments beyond human endurance. Future missions are planned, new spacecraft that will map the surface in even greater detail, that will search for active volcanoes, that will analyze the chemistry of the clouds and try to understand why Venus became what it is. Some scientists dream of distant futures where technology might terraform Venus, might cool it gradually over centuries, might restore water to a world that lost its oceans billions of years ago. Such dreams are far beyond our current capabilities, perhaps forever beyond them. But they speak to a deeper impulse, a desire to understand not just what Venus is, but what it once was, and what it might teach us about the preciousness of our own world. Leaving the furnace of Venus behind, we return home to the blue jewel that hangs in the darkness like a promise kept. Earth, our world, the only place in the vast cosmos where we know with certainty that life exists, where oceans shimmer beneath swirling clouds, where green spreads across continents in patterns of forest and field. From space, Earth glows with a soft blue light, wrapped in wisps of white, marked here and there by the brown and gold of deserts, the dark green of jungles, the white of polar ice. It is beautiful in a way that stops the breath, that makes even the most hardened astronauts pause and feel something shift inside them. Earth occupies what scientists call the Goldilocks zone, that narrow band of space around the sun where conditions are neither too hot nor too cold, but just right for liquid water to exist on a planet's surface. This distance from our star, roughly 150 million kilometers, allows temperatures to remain moderate enough that water does not boil away into space or freeze permanently into ice. Water is the key to everything we know about life. It dissolves and transports nutrients. It facilitates chemical reactions. It exists in 3 states: solid, liquid, and gas, within the temperature ranges we experience, cycling endlessly between oceans, atmosphere, ice, and living things. Without liquid water, Earth would be as barren as its neighbors. But distance alone does not explain Earth's hospitality. Venus sits not far outside the habitable zone, yet it transformed into an inferno. Mars lies near the outer edge, yet it became a frozen desert. Earth possesses something more, a delicate balance of factors that work together to maintain conditions suitable for life. Chief among these is our atmosphere, a thin blanket of gases that wraps around the planet and makes nearly everything possible. The atmosphere is astonishingly thin. If Earth were the size of an apple, the atmosphere would be no thicker than the apple's skin. Yet within that fragile layer, miracles occur. The atmosphere shields us from the sun's harshest radiation, filtering out most ultraviolet light that would otherwise sterilize the surface and damage the complex molecules that life requires. It regulates temperature, trapping enough heat to keep the planet warm, but not so much that we spiral into a runaway greenhouse effect like Venus. It distributes heat around the globe through winds and weather systems, carrying warmth from the equator toward the poles, moving moisture from oceans to land, creating the rainfall that feeds rivers and nourishes plants. The composition of our atmosphere is itself extraordinary. Roughly 78% nitrogen, 21% oxygen, and trace amounts of other gases including carbon dioxide, water vapor, and argon. The oxygen is perhaps the most remarkable component, for it did not exist in significant quantities for billions of years after Earth formed. The early atmosphere was rich in methane, ammonia, and carbon dioxide, but oxygen was scarce. Then, around 2.4 billion years ago, tiny organisms called cyanobacteria began using sunlight to convert carbon dioxide and water into sugars, releasing oxygen as a waste product. Over hundreds of millions of years, these microscopic pioneers transformed the entire atmosphere, poisoning many ancient life forms that could not tolerate oxygen, but creating conditions that would eventually allow complex life to evolve. Every breath we take connects us to those ancient microbes, to a transformation so profound it changed the color of the sky and the chemistry of stone. Beneath the atmosphere lies Earth's magnetic field, an invisible shield generated deep within the planet's core. At the center of Earth, roughly 6,000 kilometers below the surface, lies a sphere of solid iron and nickel, compressed by immense pressure into a crystal structure despite temperatures that exceed 5,000 degrees Celsius. Surrounding this inner core is an outer core of liquid iron that flows in complex patterns driven by the planet's rotation and by convection currents powered by heat escaping from the interior. These flowing currents of liquid metal generate electrical currents, and those electrical currents in turn create magnetic fields. The result is a planetary-scale dynamo, a geomagnetic field that extends thousands of kilometers into space. This magnetic field deflects the solar wind, that constant stream of charged particles flowing outward from the sun. Without it, the solar wind would gradually strip away our atmosphere, molecule by molecule, as it has done on Mars. The magnetic field channels incoming particles toward the poles, where they collide with atmospheric gases and create the shimmering curtains of light we call auroras. The northern and southern lights are more than beautiful. They are visible evidence of the invisible forces protecting our world, of the planet's iron heart beating in the darkness below. Water covers about 71% of Earth's surface, collected in vast ocean basins that hold 1.4 billion cubic kilometers of salt water. These oceans are not static. They move in great circular currents driven by wind, temperature differences, and the Coriolis effect caused by Earth's rotation. Warm water flows from the equator toward the poles, carrying heat with it. Cold water sinks and flows back toward the equator along the ocean floor. This global circulation, sometimes called the ocean conveyor belt, distributes heat around the planet and influences climate patterns across continents. The oceans also absorb enormous amounts of carbon dioxide from the atmosphere, helping to regulate the greenhouse effect and maintain temperatures within ranges conducive to life. Rain falls on land, gathers into streams, flows into rivers, and returns to the sea, completing the water cycle that has continued for billions of years. Along the way, water shapes the landscape. It carves canyons through stone. It deposits sediment in deltas. It fills lakes and underground aquifers. It seeps into soil and is drawn up through plant roots, released back into the atmosphere through leaves in a process called transpiration. Water connects everything on Earth, from the deepest ocean trenches to the highest mountain peaks, from the smallest microbe to the largest whale. The ground beneath our feet moves, though we rarely feel it. Earth is the only planet in the solar system with active plate tectonics, a slow but powerful process where the crust is broken into enormous sections called tectonic plates that float on the semi-molten mantle below. These plates move at rates measured in centimeters per year, about as fast as fingernails grow. Yet over millions of years, they travel thousands of kilometers. Where plates collide, mountains rise. The Himalayas continue to grow taller as the Indian plate pushes into the Eurasian plate, lifting rock that once lay beneath ancient seas into peaks that scrape the sky. Where plates pull apart, new crust forms as molten rock wells up from below, creating mid-ocean ridges and gradually widening ocean basins. Where one plate slides beneath another, deep ocean trenches form, and the descending plate melts, triggering volcanic activity. This constant recycling of Earth's crust serves several crucial functions. It regulates the planet's temperature over geological timescales by moving carbon between the atmosphere, oceans, and rocks. It creates diverse landscapes, from volcanic islands to towering mountain ranges to deep ocean trenches. It brings nutrients from the deep interior to the surface, enriching soils and supporting ecosystems. Without plate tectonics, Earth might have become geologically dead like Mars, its interior cooling, its magnetic field fading, its atmosphere slowly leaking away into space. Earth does not travel alone. It is accompanied by a faithful companion, the Moon, whose silver light has inspired dreams and guided calendars since before humans existed. The Moon orbits Earth at an average distance of 384,400 kilometers, close enough to appear large in our sky, close enough to exert a gravitational pull that creates tides in the oceans. Twice each day, in most places, the ocean rises and falls as the Moon's gravity tugs at the water, creating rhythms that coastal life has adapted to over millions of years. But the Moon does more than create tides. Its presence stabilizes Earth's axial tilt, keeping it steady at about 23.5 degrees. Without the Moon's gravitational influence, Earth's tilt would vary chaotically over time, swinging between extremes that would cause wild climate fluctuations. Instead, that stable tilt gives us predictable seasons as Earth orbits the Sun, the northern hemisphere tilting toward the Sun in summer and away in winter, the southern hemisphere experiencing the opposite pattern. This predictability allowed life to adapt to seasonal changes, to develop strategies for surviving cold winters and hot summers, to evolve the rich diversity we see today. Seen from space, Earth is what the astronomer Carl Sagan called a pale blue dot, a tiny speck suspended in a sunbeam, home to everyone and everything we have ever known. That perspective, that view of Earth as one small world among countless others, has changed how we think about our place in the universe. Astronauts speak of the overview effect, a cognitive shift that occurs when seeing Earth from orbit, a deep realization of the planet's fragility, its isolation, its preciousness. National boundaries disappear. Political divisions seem absurd. The thin blue line of the atmosphere appears heartbreakingly delicate against the blackness of space. Earth is approximately 4.5 billion years old, formed from the same rotating disk of gas and dust that gave birth to the Sun and all the other planets. For its first several hundred million years, it was a molten ball, bombarded by asteroids and comets, gradually cooling and forming a solid crust. The water that fills our oceans may have arrived during this violent period, delivered by icy comets and water-rich asteroids that crashed into the young planet. Or perhaps water was present all along, locked in minerals, and released as the planet heated and cooled. Either way, by 4 billion years ago, oceans existed, and within those oceans, chemistry became complex enough for life to emerge. The exact origin of life remains one of science's greatest mysteries, but we know it happened early. The oldest evidence of life dates back at least 3.5 billion years. Fossilized stromatolites built by microbial mats in shallow seas. For billions of years, life remained microscopic, single-celled, simple, yet remarkably successful. Then, around 540 million years ago, in what geologists call the Cambrian explosion, complex multicellular life suddenly diversified, filling the oceans with an astonishing variety of forms. From those ancient seas came the ancestors of everything alive today, from jellyfish to insects to birds to humans. We are latecomers to this story. Modern humans, Homo sapiens, have existed for only about 300,000 years, a mere blink in geological time. Civilization, agriculture, cities, writing, all the things we think of as human history began only about 10,000 years ago. We have walked on Earth's surface for less than 1/10,000th of its existence. Yet in that brief time, we have spread across every continent, reshaped landscapes, altered the atmosphere, and even begun to leave our planet, if only briefly, to explore the worlds beyond. Earth is both ordinary and extraordinary. It is an ordinary, rocky planet, one of countless billions that must exist in the galaxy. Yet it is extraordinary because it is the only one we know that supports life, the only place where the universe has become conscious of itself, where matter has organized into forms that can think and wonder and ask questions about existence. To be alive on Earth is to be part of something ancient and ongoing, a story written in water and stone and living cells, a story that continues with every breath, every heartbeat, every moment of awareness. Earth does not travel alone through the darkness. It is accompanied by a faithful companion, the moon, whose silver light has inspired dreams since the dawn of humanity. Night after night, it rises in the east and crosses the sky, waxing and waning in a rhythm so reliable that ancient peoples built calendars around it, marked time by its phases, told stories to explain its changing face. The moon is our closest celestial neighbor, near enough that we can see its features with the naked eye, the dark Maria and bright highlands that form patterns humans have interpreted as faces, rabbits, and legends across cultures and centuries. The moon orbits Earth at an average distance of 384,400 kilometers, though this distance varies slightly as it follows its elliptical path. At its closest approach, called perigee, It comes within 356,500 kilometers. At its farthest, apogee, it recedes to 406,700 kilometers. This variation makes the moon appear larger or smaller in our sky, sometimes by as much as 14% in diameter. When a full moon coincides with perigee, we call it a supermoon, though the difference is subtle enough that most people never notice unless they compare photographs taken months apart. How the moon came to be orbiting Earth is a story written in computer simulations and chemical analysis, in the composition of lunar rocks brought back by astronauts, and in the mathematical physics of celestial mechanics. The leading theory, one supported by decades of evidence, suggests that the moon was born from violence. About 4.5 billion years ago, when Earth was still young and molten, another protoplanet roughly the size of Mars struck our world in a glancing blow. This collision, which scientists have named the Giant Impact, was catastrophic beyond imagining. The impactor, sometimes called Theia after the Greek Titan who gave birth to the moon goddess Selene, slammed into Earth at an oblique angle. The energy released was enough to vaporize rock, to melt entire hemispheres, to send enormous quantities of debris fountaining into space. Some of this material fell back to Earth. Some escaped entirely, lost to the void. But much of it remained in orbit, a ring of molten droplets and shattered stone that gradually coalesced under its own gravity. Over thousands of years, this debris merged and cooled, forming a sphere that became our moon. Evidence for this violent origin appears in the chemical composition of lunar rocks. When Apollo astronauts returned with samples, scientists discovered that the moon's makeup closely matches Earth's mantle, the layer just beneath our crust. The moon has very little iron compared to Earth, suggesting it formed primarily from the outer layers of both bodies involved in the collision. Isotope ratios of oxygen and other elements are nearly identical between Earth and Moon, indicating they share a common heritage. Computer models that simulate the giant impact reproduce the current Earth-Moon system remarkably well, accounting for the Moon's size, its orbit, and even Earth's relatively rapid rotation. The Moon shows us only one face. This peculiar arrangement is called synchronous rotation, or tidal locking, a state where the Moon rotates once on its axis in exactly the same time it takes to orbit Earth once. The result is that the same lunar hemisphere always points toward us, while the far side remains forever hidden from view. This synchronous rotation did not happen by chance. It is the result of tidal forces acting over millions of years. When the Moon first formed, it likely rotated much faster, but Earth's gravity created tidal bulges in the Moon's slightly flexible body, pulling on the side nearest Earth and the side farthest away. These bulges wanted to align with Earth, but the Moon's rotation carried them slightly out of alignment, creating a drag that gradually slowed the rotation. Eventually, the Moon's rotation slowed until it matched its orbital period, settling into a configuration where the tidal bulges remain permanently aligned with Earth. Now, the same cratered face watches over our nights, familiar and constant, while the far side turns forever away. That far side remained a complete mystery until 1959, when the Soviet Luna 3 spacecraft flew around the Moon and transmitted the first grainy photographs back to Earth. What those images revealed surprised everyone. The far side looked dramatically different from the near side, heavily cratered with very few of the dark maria that dominate the face we see. Scientists still debate why this asymmetry exists. Perhaps the far side's thicker crust made it harder for volcanic lava to reach the surface. Perhaps the distribution of impacts was not random. Or perhaps the giant impact that created the moon left one hemisphere fundamentally different from the other. The far side is not dark, as popular language sometimes suggests. It receives just as much sunlight as the near side. It is simply hidden, turned away from our gaze, a hemisphere that remained unknown to humanity until we built machines capable of traveling beyond our world. The moon's surface tells a story of bombardment and fire. The bright highlands are ancient, formed more than 4 billion years ago, when the lunar crust first solidified from an ocean of magma that covered the young moon. These regions are saturated with craters, impact upon impact, scars layered over scars, a record of the violent early solar system, when asteroids and comets rained down in numbers that would seem apocalyptic today. The dark maria, Latin for seas, though they hold no water, are younger, formed between 3.8 and 3.1 billion years ago, when massive impacts punched through the crust and allowed molten lava to well up from the interior. This lava flooded the impact basins, cooling into smooth plains of darker basalt that contrasts with the lighter highland material. Across this landscape lies a layer of regolith, a fine powder and rubble created by billions of years of micrometeorite impacts that have ground the surface rock into particles ranging from dust to boulders. This regolith is sharp and abrasive, lacking the smoothing effects of wind and water that round grains on Earth. It sticks to everything, worked its way into every seal and joint of the Apollo spacecraft, and will pose challenges for future explorers who must design equipment to withstand its invasive properties. On July 20th, 1969, humans first set foot on another world. Neil Armstrong and Buzz Aldrin descended in the lunar module Eagle, while Michael Collins orbited overhead in the command module Columbia. Armstrong's first step onto the lunar surface, accompanied by his words about one small step and one giant leap, marked a moment of profound significance. For the first time in Earth's long history, life had left its home world and touched another celestial body. Over the next 3 years, 5 more Apollo missions landed on the moon. 12 humans walked on its surface, conducted experiments, collected rocks, took photographs, and experienced the profound isolation and beauty of standing on an airless world where Earth hangs in a black sky. The samples they brought back, 382 kilograms of lunar rock and soil, transformed our understanding of the moon and the early solar system. By analyzing these rocks, scientists determined the moon's age, confirmed theories about its formation, discovered evidence of the late heavy bombardment that scarred the inner solar system around 3.9 billion years ago, and learned that the moon has been geologically dead for billions of years, its interior cooled, its volcanic activity long ceased. The footprints left by those 12 astronauts remain on the lunar surface today, preserved in the airless environment where no wind erodes and no rain washes away. They will remain for millions of years. Silent testimony to the brief moment when humans ventured beyond their cradle. The moon is slowly drifting away from Earth. Precise laser measurements bounced off reflectors left by Apollo astronauts, reveal that our companion recedes at about 3.8 centimeters per year. This recession is caused by the same tidal forces that locked the moon's rotation. Just as the moon raises tides in Earth's oceans, Earth raises tides in the moon, though the moon's rigidity makes these tidal bulges much smaller. But Earth also raises tidal bulges in Earth itself, in the oceans, and even in the flexible crust. These bulges are carried ahead of the moon by Earth's faster rotation, and their gravitational pull acts on the moon, gradually accelerating it in its orbit. As the moon gains energy, it moves into a higher, slower orbit, gradually spiraling away from Earth. Billions of years ago, the moon was much closer, perhaps only 20,000 kilometers away, and it moved across the sky much faster. The tides it raised would have been enormous, hundreds of meters high, surging across the young Earth's oceans with tremendous force. Earth's rotation was also faster then, the day lasting perhaps only 5 or 6 hours. Over time, the moon's tidal drag has slowed Earth's rotation, lengthening our days, while the moon has retreated to its current distance. This process continues. In the distant future, billions of years from now, Earth's rotation will slow enough that it too becomes tidally locked to the moon, always showing the same face to its companion. But this will take longer than the sun has left in its current state, so it may never happen before our star exhausts its fuel and transforms into something else entirely. The moon governs rhythms on Earth that extend far beyond the tides. Many marine organisms time their reproduction to lunar phases. Certain species of coral spawn simultaneously on specific nights following a full moon, releasing eggs and sperm into the water in such numbers that predators cannot possibly eat them all. Sea turtles nest on beaches during high tides associated with full and new moons. Even some land animals show behaviors linked to lunar cycles, though the mechanisms are often mysterious. For humans, the moon provided the first calendar, a way to track time in units longer than a day, but shorter than a year. Many cultures developed lunar calendars that tracked the moon's phases, and even our modern solar calendar preserves lunar influence in the word month, derived from moon. Future plans for the moon include permanent human presence. NASA's Artemis program aims to return humans to the lunar surface in the coming years, this time to establish a sustainable presence with habitats, rovers, and infrastructure that would allow crews to stay for extended periods. The lunar South Pole attracts particular interest because permanently shadowed craters there contain water ice, a resource that could be mined for drinking water, oxygen, and even rocket fuel. International space agencies and private companies envision the moon as a stepping stone for deeper space exploration, a place to test technologies and develop capabilities needed for eventual missions to Mars and beyond. Standing on the moon and looking back at Earth would offer a view that only 12 humans have ever experienced directly, though many more have seen it through photographs and video. Earth hangs in the lunar sky, never rising or setting from any given location due to tidal locking, appearing about 4 times larger in diameter than the moon appears from Earth. It goes through phases just as the moon does from our perspective, waxing and waning from new Earth to full Earth over the course of a lunar day. The colors are vivid against the blackness. Swirls of white cloud, deep blue oceans, brown and green continents. From the moon, Earth looks fragile and isolated, a small sanctuary of warmth and life, surrounded by the cold emptiness of space. Beyond Earth's gentle companion lies a world that has captivated human imagination for centuries, a planet whose rust-red color made ancient peoples name it for the god of war. Mars hangs in the night sky like a drop of blood among the silver stars, its ruddy hue unmistakable, its presence both familiar and alien. Of all the planets in our solar system, Mars is the one that most resembles Earth. Yet it is hauntingly different. A world that speaks of lost possibilities, of water that once flowed and air that once filled valleys, now silent and still. Mars is smaller than Earth, roughly half our planet's diameter, with only about 38% of Earth's surface gravity. If you could stand on its rusty plains, you would feel light, almost buoyant, able to leap several times higher than on Earth. The planet takes 687 Earth days to complete one orbit around the Sun, giving it a year nearly twice as long as ours. But a Martian day, called a sol, lasts 24 hours and 37 minutes, remarkably similar to Earth's rotation. This near match means that future explorers will find their circadian rhythms easily adapting to Martian time, one of the few conveniences that Mars offers to potential visitors. The rusty color that defines Mars comes from iron oxide, the same compound that forms rust on Earth. The entire surface is covered in a fine dust, rich in oxidized iron, giving the soil and rocks their characteristic reddish-brown hue. Wind carries this dust across the planet in storms that can grow large enough to engulf entire hemispheres, turning the thin atmosphere into an opaque haze that blocks sunlight for months. Even on calm days, dust devils dance across the plains, spinning columns of red particles hundreds of meters high. From orbit, spacecraft have watched these dust devils trace spiraling patterns across dunes and craters, brief moments of movement in an otherwise still landscape. The atmosphere of Mars is thin, almost nothing compared to Earth's protective blanket. Surface pressure averages about 0.6% of Earth's atmospheric pressure, equivalent to standing 35 kilometers above Earth's surface, well above the altitude where aircraft can fly. This thin atmosphere is composed mostly of carbon dioxide, with traces of nitrogen and argon, but no breathable oxygen. A human standing on Mars without a pressure suit would lose consciousness within seconds as the low pressure caused their blood to boil at body temperature. The thin air provides little insulation, allowing temperatures to swing wildly between day and night. At the equator during summer, afternoon temperatures might reach a pleasant 20 degrees Celsius, but by midnight, they plummet to -70 degrees Celsius or lower. Near the poles, temperatures can drop below -125 degrees Celsius, cold enough to freeze carbon dioxide from the atmosphere into dry ice. Mars is a world of spectacular geological features that dwarf anything on Earth. Rising from the Tharsis Plateau stands Olympus Mons, the tallest volcano in the solar system. This shield volcano climbs 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest, with a base so wide, roughly 600 kilometers across, that it would cover an area the size of Arizona. The summit contains a caldera 80 kilometers wide, formed by the collapse of the magma chamber beneath. If you stood on the slopes of Olympus Mons, the volcano would extend beyond the horizon in every direction. Its incline so gentle, only about 5 degrees on average, that you might not even realize you were climbing a mountain. Yet from space, Olympus Mons dominates the landscape, a titanic monument to volcanic forces that shaped Mars billions of years ago. Not far from Olympus Mons stretches another marvel, Valles Marineris, a canyon system so vast it makes Earth's Grand Canyon seem like a modest scratch in the ground. This great rift extends for more than 4,000 kilometers along Mars's equator, roughly the distance across the continental United States. In places, the canyon plunges 7 kilometers deep and spans 200 kilometers wide. If you placed Valles Marineris on Earth, it would stretch from New York to Los Angeles. The canyon formed not from water erosion like river canyons on Earth, but from tectonic stresses that pulled the Martian crust apart billions of years ago. Landslides have carved its walls into intricate patterns, and in some regions, layered sediments suggest that water or ice once filled portions of the canyon, leaving deposits that now appear as distinct bands visible from orbit. Water is the central mystery of Mars, the question that drives much of our exploration. Today, Mars is cold and dry, its surface scoured by radiation, its atmosphere too thin to support liquid water. Any water exposed on the surface would either freeze or sublimate directly into vapor within seconds. Yet everywhere spacecraft look, they find evidence that water once flowed abundantly across the Martian surface. Ancient riverbeds snake across highlands, their branching patterns unmistakable. Delta deposits fan out where rivers once emptied into lakes that have long since vanished. Minerals that form only in the presence of water, clays and sulfates and carbonates appear in vast deposits. Some regions show features that look remarkably like shorelines, as if an ocean once filled the northern lowlands, though this remains debated. The story these features tell is one of a different Mars, a younger planet that was warmer and wetter. Between 3.8 and 3.5 billion years ago, during a period geologists call the Noachian era, Mars may have had a thicker atmosphere, one capable of trapping enough heat to keep surface temperatures above freezing. Rain might have fallen from clouds, filling rivers that carved the valleys we see today. Lakes and perhaps even an ocean might have covered portions of the surface. This ancient Mars might have been habitable, might have offered conditions where life could arise, sheltered in warm water, feeding on minerals and sunlight. What happened to that world remains one of planetary science's great puzzles. Mars lost its magnetic field early in its history. Unlike Earth, whose molten outer core generates a protective magnetic field, Mars's interior cooled relatively quickly. Once the dynamo in its core shut down, the planet became vulnerable to the solar wind, that constant stream of charged particles flowing from the sun. Without a magnetic field to deflect them, these particles stripped away the Martian atmosphere molecule by molecule over hundreds of millions of years. As the atmosphere thinned, surface pressure dropped, temperatures fell, and the water that once flowed on the surface either froze, sublimated into space, or soaked into the ground. Today, Mars is a desert world, its atmosphere too thin to sustain liquid water, its surface bombarded by radiation that would be lethal to any unprotected life. But the water did not entirely disappear. Much of it remains, locked in ice. The polar ice caps of Mars are visible even through small telescopes, bright white patches that grow and shrink with the seasons. The northern cap is primarily water ice, while the southern cap consists of water ice overlain by a seasonal layer of frozen carbon dioxide. During winter, carbon dioxide from the atmosphere freezes onto the poles, causing the caps to expand. In summer, this dry ice sublimes back into gas, revealing the permanent water ice beneath. These caps contain enough frozen water to cover the entire planet in a layer 10 meters deep if melted. Water ice also exists underground, buried beneath the surface across much of the planet. Radar instruments aboard orbiting spacecraft have detected vast deposits of subsurface ice, particularly at high latitudes. In 2008, the Phoenix lander dug into the Martian soil and found bright white ice just centimeters beneath the surface. Some scientists believe that vast glaciers of ice, covered by protective layers of dust and rock, flow slowly in the mid-latitudes, hidden evidence of a more recent ice age on Mars. Where this ice exists, future human explorers might find the water they need to sustain a settlement, to grow food, to manufacture fuel for the return journey to Earth. The question of whether life ever arose on Mars, or might still exist in protected niches beneath the surface, drives much of our exploration. In 1996, scientists announced that a meteorite from Mars, found in Antarctica, contained structures that might be fossilized bacteria. The claim sparked intense debate and has since been largely dismissed, but it highlighted the profound implications of finding even simple microbes on another world. If life arose independently on Mars, it would suggest that life is common in the universe, that wherever conditions permit, chemistry finds a way to become biology. Robotic explorers have been searching for signs of past or present life for decades. The Viking landers in 1976 conducted experiments designed to detect metabolic activity in Martian soil. The results were ambiguous, neither confirming nor ruling out the presence of microorganisms. More recent missions have focused on understanding Mars's history and identifying environments where life might once have existed. The Spirit and Opportunity rovers, which landed in 2004, found conclusive evidence of past water. Opportunity discovered tiny spheres of hematite, nicknamed blueberries, that form in standing water. It analyzed rocks that once sat at the bottom of an ancient sea, slowly accumulating layers of sediment. Curiosity, which landed in Gale Crater in 2012, has spent more than a decade climbing through layers of sedimentary rock that record Mars's transition from a wetter to a drier world. It has detected organic molecules, the carbon-based building blocks of life, though these could have formed through non-biological processes or arrived via meteorites. Curiosity has measured methane in the atmosphere, a gas that on Earth is often produced by living organisms, though geological processes can also create it. The methane appears sporadically, its source and fate unknown. A tantalizing mystery. Perseverance, the newest rover, landed in Jezero Crater in 2021, a location chosen because orbital images show clear evidence of an ancient river delta. For billions of years, a river flowed into this crater, depositing layers of sediment that might preserve fossils if life ever existed there. Perseverance is collecting samples of rock and soil, sealing them in tubes that will be left on the surface for a future mission to retrieve and return to Earth. These samples, analyzed in laboratories with instruments far more sophisticated than anything we can send to Mars, might finally answer the question of whether life ever gained a foothold on our neighboring world. The dream of sending humans to Mars has inspired generations. The challenges are immense. A journey to Mars takes between 6 and 9 months, depending on the orbital alignment of the planets, far longer than the 3 days to reach the Moon. Astronauts would face prolonged exposure to cosmic radiation and microgravity, both hazardous to human health. They would need to bring or manufacture everything they need to survive: oxygen, water, food, fuel, on a world with no breathable air, no liquid water, and minimal resources. Dust storms could damage equipment. The psychological strain of isolation, living in a small habitat millions of kilometers from help, could test even the most trained crews. Yet despite these obstacles, plans are advancing. Space agencies and private companies are developing the rockets, habitats, and life support systems that would make a crewed Mars mission possible, perhaps within the next 2 decades. On Mars, the sky is not blue, but a butterscotch tan during the day, colored by the fine dust suspended in the atmosphere. At sunset, the colors reverse. While the sky near the sun glows blue, the rest of the sky turns pink and red as dust scatters the shorter wavelengths. The sun itself appears about 2/3 the size it does from Earth, dimmer and colder. Shadows are sharp in the thin air, and distances are deceptive, the clarity making faraway mountains seem closer than they are. Silence would be profound, broken only by the faint whisper of wind, for the thin atmosphere carries sound weakly. You would feel light, almost floating with each step, and looking up at night, you would see Earth, a pale blue star, accompanied by an even smaller point of light, the Moon, both of them faint and distant, a reminder of how far you had traveled. Mars is both a destination and a mirror. It shows us what Earth might have become if conditions had been slightly different, if our planet had been smaller, if we had lost our magnetic field, if the delicate balance that sustains our world had tipped in another direction. It reminds us that habitability is not permanent, that worlds can change, that the line between a living planet and a dead one is thinner than we might wish. And yet Mars also offers hope, the possibility that life might arise in multiple places, that we might one day walk on another world, that humanity's future might extend beyond the single fragile planet we call home. Leaving the rocky inner worlds behind, we cross an invisible boundary, a region where the architecture of the solar system shifts from solid ground to scattered fragments. Between Mars and Jupiter lies the asteroid belt, a vast expanse spanning roughly 150 million kilometers that holds millions of rocky bodies, remnants from the solar system's formation, pieces of a world that never came to be. The name conjures images from science fiction, dense fields of tumbling rocks that spacecraft must navigate with split-second timing. But the reality is far more subtle, far emptier than imagination suggests. The asteroid belt is mostly space. If you were to travel through it, you would likely see nothing but darkness stretching in every direction, stars scattered across the black. The asteroids themselves are separated by such enormous distances, millions of kilometers on average, that spacecraft routinely pass through the belt without coming close to anything larger than a grain of sand. The total mass of all asteroids combined amounts to only about 4% of the Moon's mass, a collection of fragments that, if gathered together, would form a body smaller than our lunar companion. Yet within this seemingly empty region drifts a population of objects that tells the story of the early solar system, preserved in stone and ice, waiting to share their secrets. These asteroids are not uniform. They come in different compositions, different sizes, different shapes, each one a unique survivor of the violent processes that shaped the planets. Some are made of stone, silicate minerals similar to those found in Earth's crust. Others are metallic, primarily iron and nickel, likely fragments of the cores of larger bodies that broke apart in ancient collisions. Still others are carbonaceous, dark and rich in carbon compounds and water, among the most primitive objects in the solar system, their chemistry largely unchanged since the solar nebula first condensed into solid matter 4.6 billion years ago. The largest object in the asteroid belt is Ceres, massive enough to pull itself into a spherical shape through its own gravity, a feat that earned it the designation of dwarf planet. Ceres measures about 940 kilometers in diameter, accounting for roughly a third of the asteroid belt's total mass. For decades, it was known only as a point of light moving against the stars, its surface a mystery. Then in 2015, NASA's Dawn spacecraft arrived, settling into orbit and revealing a world far stranger than anyone expected. Ceres' surface is ancient and heavily cratered, dark gray and dusty, marked by countless impacts spanning billions of years. But within some of these craters lie bright white deposits that shine like beacons against the darker terrain. The brightest of these, located in Ocketer Crater, puzzled scientists when first observed. Spectrographic analysis revealed them to be sodium carbonate, a salt compound that forms when briny water evaporates. The implications are profound. Ceres must have, or perhaps still has, liquid water beneath its surface, a subsurface ocean or pockets of brine that occasionally seep upward through cracks, reaching the surface where they freeze and evaporate, leaving behind these bright salt deposits. Dawn's instruments detected organic molecules on Ceres' surface, complex carbon-based compounds that are the building blocks of life, though not life itself. These organics, combined with water and minerals, make Ceres a place of surprising complexity. Some scientists now believe that Ceres might harbor environments beneath its icy crust where conditions could theoretically support microbial life, though no mission has yet been designed to drill through and explore those hidden depths. Ceres reminds us that even small worlds, even fragments in a belt of debris, can hold mysteries that challenge our understanding of where life might arise. Vesta, the second largest asteroid, could hardly be more different. Where Ceres is dark and possibly wet, Vesta is bright and bone-dry. A battered protoplanet that almost became something greater. Vesta measures about 525 kilometers in diameter, large enough that it differentiated early in its history, meaning it melted and separated into distinct layers. An iron core, a rocky mantle, and a basaltic crust formed from volcanic activity. Essentially, Vesta began the process of becoming a true planet but never completed it, frozen in an intermediate state when Jupiter's gravity stirred the asteroid belt and prevented further growth. Dawn visited Vesta before continuing to Ceres. And the images it returned showed a world of dramatic contrasts. A massive impact crater dominates the southern hemisphere, so large that it excavated material from deep within Vesta's interior and blasted debris across the solar system. Some of this debris eventually fell to Earth as meteorites. Scientists have identified a class of meteorites called head meteorites, Howardites, Eucrites, and Diogenites, whose composition matches Vesta so precisely that we know with certainty they came from this distant asteroid. These meteorites allow us to study a piece of Vesta in laboratories, to analyze its chemistry and age, to understand the processes that occurred within it billions of years ago. The asteroid belt exists because of Jupiter. In the early solar system, as planets formed from the swirling disk of dust and gas around the young sun, material in the region between Mars and Jupiter began to clump together, following the same process that built Earth and the other rocky worlds. But Jupiter grew massive quickly, and its immense gravity stirred the asteroid belt violently, increasing the velocities of objects orbiting there. Instead of gently colliding and sticking together to form larger bodies, asteroids began smashing into each other at speeds that shattered them into fragments. Jupiter's gravitational influence also scattered many objects out of the belt entirely, ejecting them into the inner solar system, or flinging them toward the outer planets. What remains today is a remnant population, a shadow of what might have been a planet, preserved in fragments because Jupiter's presence prevented coalescence. These fragments span an enormous range of sizes. The largest, Ceres and Vesta, are spherical or nearly so. Hundreds more measure over 100 kilometers across. Substantial bodies with their own complex histories. Tens of thousands exceed 10 kilometers, and millions are smaller still, down to house-sized boulders and gravel and dust. Even at this scale, each asteroid is an individual world, shaped by its own history of collisions and exposure to space. Some asteroids are solid chunks of rock or metal. Others are rubble piles, loose collections of fragments held together by weak gravity, their interiors more like gravel bags than solid stone. Some asteroids have moons. Ida, visited by the Galileo spacecraft in 1993, revealed a tiny companion named Dactyl, orbiting just 90 kilometers away, the first asteroid moon ever discovered. Since then, hundreds more binary and even triple asteroid systems have been found. Small worlds accompanied by even smaller companions, dancing together through the void. Some asteroids rotate rapidly, completing a turn in just a few hours. Others tumble chaotically, their rotation axes precessing like wobbling tops, the result of asymmetric shapes and past collisions. Not all asteroids stay safely in the belt. Gravitational interactions and collisions occasionally nudge objects into orbits that cross the paths of the inner planets. These are the near-Earth asteroids, bodies whose trajectories bring them close to our world, sometimes alarmingly so. Thousands have been cataloged, their orbits calculated and monitored. Most will never hit Earth, but the possibility exists, as evidenced by the impact 66 million years ago that contributed to the extinction of the dinosaurs. That impactor was likely an asteroid about 10 kilometers wide, and the energy released by its collision excavated the Chicxulub crater and triggered environmental catastrophes that reshaped life on Earth. Today, astronomers scan the skies nightly, tracking near-Earth asteroids, calculating their trajectories, assessing the risk they pose. For objects on potential collision courses, decades or centuries in the future, we now have the technology to consider deflection missions, spacecraft that could nudge an asteroid slightly, changing its path enough to miss Earth entirely. In 2022, NASA's DART mission deliberately crashed into the small asteroid moon Dimorphos, successfully altering its orbit around the larger asteroid Didymos, proving that humanity possesses the capability to defend itself against cosmic impacts if given sufficient warning. But asteroids are not only threats, they are also opportunities. Many asteroids contain valuable resources, water ice that could be split into hydrogen and oxygen for rocket fuel, metals like platinum and gold in concentrations far higher than anywhere on Earth, rare Earth elements essential for modern technology. Some visionaries imagine a future where asteroid mining becomes economically viable, where spacecraft harvest resources from these drifting mountains of ore and ice, where the raw materials for building habitats and fuel depots in space come not from Earth's gravity well, but from the asteroid belt itself. Such plans remain speculative, the economics uncertain, the technology unproven, but the resources are real, waiting in the darkness. Missions to asteroids have revealed them to be far more interesting than mere rocks in space. Japan's Hayabusa 2 mission visited the asteroid Ryugu, a dark carbonaceous object shaped like a spinning top, and collected samples from its surface. When those samples returned to Earth in 2020, scientists discovered pristine material, rich in organic compounds and amino acids, the chemical precursors to life. NASA's OSIRIS-REx performed a similar feat at asteroid Bennu, briefly touching down to collect a sample that returned to Earth in 2023. Analysis of Bennu's material is ongoing, but early results confirm the presence of water-bearing minerals and complex organic molecules. These asteroids may have delivered the ingredients for life to early Earth, seeding our planet with water and carbon compounds during the heavy bombardment period billions of years ago. The asteroid belt is also a time capsule. Because these objects never formed into a planet, because they never experienced the geological processes that reshape planetary interiors and surfaces, they preserve materials from the solar system's birth. Their compositions vary depending on where they formed in the solar nebula. Those closer to the Sun tend to be rockier and drier, having formed in warmer regions. Those farther out contain more water and organic compounds, condensed from the cooler outer reaches. By studying asteroids, we learn about the distribution of materials in the early solar system, about the temperature gradients and chemical processes that operated as the planets assembled. Imagine drifting through the asteroid belt in a spacecraft, engines quiet, solar panels extended toward the distant sun. Days might pass before you encountered anything large enough to see with the naked eye. Then, gradually, a silhouette would emerge against the stars, growing from a point to a shape, revealing itself as a tumbling mountain of stone or metal, pitted and scarred, slowly rotating in the silence. Its surface would be gray, or brown, or black, covered in a fine dust called regolith, softened by eons of micrometeorite impacts. Craters of all sizes would overlap, each one a record of an ancient collision. And then it would recede, slipping back into invisibility as the distance grew, leaving you once more in the emptiness, with only the stars and the faint glow of Jupiter ahead, growing brighter with each passing day. The asteroid belt marks a boundary, a transition. Behind lies the realm of rock and metal, the terrestrial planets with their solid surfaces and thin atmospheres. Ahead lies the realm of giants, worlds so massive they never formed solid surfaces, planets composed of gas and liquid under pressures that transform matter into states we struggle to imagine. Beyond the belt of ancient stones, we approach the realm of giants, and the first world we encounter commands attention with its sheer immensity. Jupiter, the king of planets. A sphere of swirling clouds so massive that more than 1/1300 Earths could fit within its volume. A world that contains more mass than all the other planets, moons, asteroids, and comets in the solar system combined. From a distance, Jupiter glows with reflected sunlight, a bright beacon that ancient astronomers recognized as something special, something different from the fixed stars. They named it for the ruler of their gods, and the name has proven fitting. Jupiter is a giant in every sense, a world that shaped the solar system's architecture and continues to influence the dance of planets and asteroids across billions of kilometers of space. Jupiter has no solid surface. If you could somehow descend through its atmosphere, you would fall through layers of gas that gradually become thicker, denser, hotter, until the distinction between atmosphere and interior blurs into something that is neither gas, nor liquid, nor solid, but all three at once. The planet is composed primarily of hydrogen and helium, the lightest elements, the same materials that make up the Sun. In fact, Jupiter is sometimes described as a failed star, a world that might have ignited nuclear fusion in its core if only it had been about 80 times more massive. But Jupiter is not a star, not even close. It radiates more heat than it receives from the Sun, leftover warmth from its formation billions of years ago. But this heat comes from gravitational contraction, not fusion. Jupiter is definitively a planet, though a planet unlike any in the inner solar system. The visible face of Jupiter is a tapestry of bands and swirls, parallel stripes of color that wrap around the planet in latitudes. The light-colored zones are regions of rising gas, cooler clouds of ammonia, ice crystals floating high in the atmosphere. The darker belts are areas where gas descends, warmer and deeper, revealing layers colored by complex organic compounds created by sunlight and lightning acting on methane and ammonia. These bands do not remain still. They flow like rivers in the sky, driven by Jupiter's rapid rotation. The planet spins faster than any other in the solar system, completing one full rotation in just under 10 hours. This furious spin flattens Jupiter noticeably at its poles and bulges its equator outward, creating an oblate shape visible even through modest telescopes. Within these bands, storms rage with a violence that dwarfs anything Earth experiences. The most famous is the Great Red Spot, an anticyclonic storm that has persisted for at least 350 years, perhaps much longer. When astronomers first began detailed observations of Jupiter in the 1600s, they noted a prominent oval marking, and it has appeared in nearly every observation since. The Great Red Spot is enormous, currently measuring about 16,000 kilometers across, wider than Earth's diameter, though it has been shrinking gradually over the past century. Within this storm, winds reach speeds of 400 kilometers per hour, rotating counterclockwise as gases spiral around a high-pressure center. The storm's reddish color comes from complex chemicals brought up from deeper layers, possibly phosphorus compounds or organic molecules, though the exact chemistry remains debated. The Great Red Spot is not alone. Jupiter's atmosphere hosts dozens of smaller storms, white ovals and brown barges, ephemeral features that appear and disappear over months or years. Lightning flashes in the clouds, bolts far more powerful than terrestrial lightning, illuminating the darkness on Jupiter's night side in brilliant bursts. Thunder would be deafening if anyone could survive to hear it. But the violence of Jupiter's weather is played out in a realm where no human could exist, where pressures and temperatures would destroy any visitor long before they reached whatever passes for the planet's interior. Descending deeper into Jupiter would take you through layers of increasing strangeness. About 1,000 kilometers below the visible cloud tops, pressure becomes so intense that hydrogen is compressed into a liquid. You would fall through an ocean of liquid hydrogen, not the cold cryogenic liquid we create in laboratories, but hydrogen hot and dense, pressed together by the weight of the atmosphere above. Deeper still, perhaps 10,000 kilometers down, pressure reaches millions of times Earth's atmospheric pressure, and hydrogen transforms into something exotic called metallic hydrogen. In this state, hydrogen atoms are squeezed so tightly that their electrons break free and flow like electrons in a metal, making the hydrogen electrically conductive. This vast layer of metallic hydrogen, stirred by Jupiter's rapid rotation and heated from below, generates the most powerful magnetic field of any planet in the solar system. Jupiter's magnetic field is immense, extending millions of kilometers into space, far enough to engulf several of its largest moons in a protective magnetosphere. Within this magnetic cocoon, charged particles from the solar wind become trapped, spiraling along magnetic field lines and creating radiation belts far more intense than Earth's Van Allen belts. The radiation environment near Jupiter is lethal, posing serious challenges for any spacecraft that ventures close. The Galileo probe, which orbited Jupiter from 1995 to 2003, endured radiation doses equivalent to being exposed to millions of chest X-rays, and its electronics gradually degraded until mission controllers deliberately crashed it into Jupiter to prevent any possibility of contaminating the potentially habitable moon Europa. At Jupiter's core, if such a thing can be said to exist, conditions become almost unimaginable. Temperatures may reach 24,000 degrees Celsius, hotter than the surface of the Sun, and pressures approach 100 million times Earth's atmospheric pressure. What exists there, whether a solid core of rock and ice or a diffuse region where elements dissolve into the metallic hydrogen, remains uncertain. The Juno spacecraft, which arrived at Jupiter in 2016, has been measuring the planet's gravitational field with unprecedented precision, trying to tease out the structure of the interior by observing how mass is distributed. Early results suggest Jupiter may have a diluted core, perhaps partially dissolved or mixed with the surrounding layers, a complexity that challenges models of how giant planets form and evolve. Jupiter plays a crucial role in the solar system as a cosmic shield. Its immense gravity deflects or captures many comets and asteroids that would otherwise fall into the inner solar system, reducing the number of impacts on Earth and the other rocky planets. In 1994, astronomers witnessed this protective role dramatically when comet Shoemaker-Levy 9, broken into fragments by Jupiter's tidal forces during a previous close approach, crashed into the planet in a series of spectacular impacts. Each fragment struck with the force of millions of nuclear bombs, creating dark scars in Jupiter's atmosphere that persisted for months. The impacts were visible from Earth through backyard telescopes, a reminder of the violence that still occurs in our solar system, and of Jupiter's role in absorbing some of that violence before it reaches us. But Jupiter is more than a solitary giant. It is accompanied by a miniature solar system of moons, at least 95 known satellites orbiting the planet, ranging from tiny captured asteroids a few kilometers across to worlds larger than Mercury. The 4 largest moons, discovered by Galileo Galilei in 1610, are worlds in their own right, each unique, each fascinating, each revealing something about the diversity of planetary bodies. Io, the innermost of the Galilean moons, is the most volcanically active body in the solar system. Its surface is painted in sulfurous yellows, oranges, and reds, colors that come from sulfur and sulfur compounds erupted from hundreds of active volcanoes. Io experiences this volcanic fury because of tidal heating. As Io orbits Jupiter, the gravitational pulls from Jupiter and the other Galilean moons flex the moon's interior like a stress ball being squeezed rhythmically. This constant flexing generates enormous heat through friction, melting Io's interior and driving volcanic eruptions that continuously resurface the moon. Some of Io's volcanoes erupt with such force that plumes of gas and particles fountain 300 kilometers above the surface, visible to passing spacecraft. The moon has essentially no impact craters because volcanic activity buries them faster than new ones can form, making Io one of the youngest surfaces in the solar system, despite being billions of years old. Europa, the next moon outward, could hardly be more different. Its surface is a shell of water ice, smooth and bright, crisscrossed by a network of dark cracks and ridges that make it look like a fractured eggshell. Beneath this icy crust, scientists believe, lies a global ocean of liquid water, perhaps 100 kilometers deep. containing more water than all of Earth's oceans combined. This ocean is kept liquid by tidal heating, though less intense than Io experiences. The evidence for Europa's ocean comes from multiple sources. Magnetic field measurements suggesting a conductive layer beneath the surface. Surface features that appear to be floating ice rafts that have broken apart and refrozen, and geysers of water vapor observed erupting from cracks near the South Pole. Europa has become one of the most exciting targets in the search for extraterrestrial life, where there is liquid water in contact with rock, where tidal heating provides energy, where organic compounds delivered by meteorites accumulate over billions of years. Conditions might exist for life to emerge. The ocean floor of Europa might host hydrothermal vents similar to those on Earth's ocean floor, environments where life thrives on chemical energy rather than sunlight. Future missions, including NASA's Europa Clipper and ESA's JUICE spacecraft, will study Europa in detail, measuring the thickness of its ice shell, analyzing the composition of its surface and geysers, searching for evidence that this hidden ocean might harbor life. Ganymede, the largest moon in the solar system, exceeds even Mercury in size. It is the only moon known to generate its own magnetic field, suggesting it has a liquid iron core despite being so cold and distant from the sun. Like Europa, Ganymede likely has a subsurface ocean, perhaps sandwiched between layers of ice at different pressures. Its surface shows a mix of ancient dark terrain, heavily cratered and ancient, and younger bright terrain, marked by grooves and ridges where tectonic activity has resurfaced portions of the moon. Ganymede is a world of quiet complexity, less dramatic than volcanic Io or potentially habitable Europa, but no less scientifically valuable. Callisto, the outermost Galilean moon, orbits beyond the most intense radiation belts and shows a surface saturated with impact craters, one of the oldest surfaces in the solar system. No geological process has erased these scars. Callisto simply accumulated impacts for billions of years, recording the bombardment history of the outer solar system in its ice. Yet even Callisto may hide a subsurface ocean, detected through subtle variations in its magnetic field during flybys. The Galilean moons, taken together, form a laboratory for comparative planetology, 4 worlds formed in the same region from the same materials, yet each shaped by its position and interactions into something unique. The Juno spacecraft continues to orbit Jupiter, diving repeatedly through the radiation belts, swooping close to the cloud tops, mapping the gravitational and magnetic fields, peering through the clouds with microwave instruments to see the depths below. It has revealed that Jupiter's bands and zones extend thousands of kilometers deep, that the weather we observe on the surface is connected to massive flows in the interior. It has measured Jupiter's polar regions for the first time, discovering swirling cyclones arranged in geometric patterns around each pole, storms locked in formation by some mechanism not yet understood. With each orbit, Juno returns data that challenges and refines our understanding, showing that even familiar worlds hold surprises. From Io, one of its moons, Jupiter would fill half the sky, a vast curved wall of swirling colors, the great red spot drifting across like a great eye watching. The phases would cycle as Io orbits, from new Jupiter to full Jupiter, the planet reflecting sunlight so brightly that night would barely exist. From Europa, the view would be similar, but the planet would loom slightly smaller, though still enormous. Shadows of other moons would occasionally transit across Jupiter's face, dark circles sliding across the clouds. And always, the planet would be silent from your perspective, its storms and lightning and winds playing out in vacuum, a spectacle of motion and violence made surreal by the absence of sound. Continuing outward through the cold outer reaches, we arrive at the jewel of the solar system, a world so beautiful that even hardened scientists pause when first seeing its image, overcome by the simple elegance of its form. Saturn, the ringed wonder, the second largest planet, famous not for its size alone, but for the magnificent system of rings that encircles it. Bands of ice and rock that catch sunlight and glow like a halo around the golden sphere. No other planet possesses rings quite like Saturn's, so extensive, so bright, so achingly beautiful that they have inspired wonder since Galileo first glimpsed them through his primitive telescope in 1610 and struggled to understand what he was seeing. Saturn is a gas giant like Jupiter, composed primarily of hydrogen and helium, with no solid surface to stand upon. It measures about 120,000 kilometers across its equator, 9 times wider than Earth, though its volume could contain more than 760 Earths. Yet despite this size, Saturn is remarkably light. Its average density is less than that of water, meaning if you could find an ocean large enough, Saturn would float. This low density comes from its composition, mostly the lightest elements in the universe, and from its distance from the Sun, where cold temperatures prevent these gases from compressing as tightly as they do in Jupiter's deeper gravity well. Like Jupiter, Saturn rotates rapidly, completing one turn in just over 10.5 hours. This swift rotation flattens the planet noticeably, creating a bulge at the equator and making Saturn the most oblate of all the planets. If you could measure from pole to pole and compare it to the equatorial diameter, you would find Saturn is about 10% narrower in one direction than the other, a distortion visible even through small telescopes. This rapid spin also drives powerful winds in Saturn's atmosphere, jet streams that race around the planet at speeds exceeding 1,800 kilometers per hour near the equator, faster than any winds on Jupiter, faster than the speed of sound on Earth. The atmosphere of Saturn displays banded patterns similar to Jupiter's, though far more subtle, the colors muted and soft compared to Jupiter's dramatic contrasts. Pale yellows and creams dominate, with hints of gold near the equator, colors that come from ammonia crystals in the upper atmosphere, and traces of phosphine and hydrocarbons deeper down. Occasionally, great storms erupt in Saturn's clouds, massive disturbances that can grow large enough to encircle the entire planet. These storms appear roughly once every Saturnian year, which lasts 29.5 Earth years, and are known as Great White Spots because of the bright clouds of ammonia ice they produce. The most recent major storm erupted in 2010, beginning as a small bright spot and expanding within weeks into a turbulent band that wrapped around the northern hemisphere, generating lightning flashes thousands of times more powerful than terrestrial lightning. At Saturn's North Pole, spacecraft have revealed one of the solar system's strangest features, a massive hexagonal jet stream that maintains its six-sided shape with remarkable stability. Each side of the hexagon spans about 13,800 kilometers, wider than Earth's diameter. Within this hexagon, a powerful storm churns, winds rotating in a tight vortex. The hexagonal shape appears to be maintained by the interaction of different wind speeds at different latitudes, a pattern that emerges naturally from the fluid dynamics of Saturn's atmosphere, yet looks so geometric, so artificial, that it seems almost impossible. The hexagon has persisted for decades, perhaps centuries, a reminder that nature can create patterns that rival any human design in their regularity and beauty. But it is Saturn's rings that truly captivate, that define this world in human imagination. The ring system extends outward from just above the planet's clouds to a distance of about 280,000 kilometers. Yet the rings are extraordinarily thin, in most places less than 10 meters thick, vertically, sometimes as thin as a few meters. If you could scale Saturn and its rings down to the size of a paper plate, the rings would be thinner than a sheet of paper, a vast horizontal expanse with almost no vertical dimension. This thinness results from collisions among ring particles that gradually flatten any vertical motion, leaving the particles orbiting in an almost perfectly flat plane. The rings are composed primarily of water ice, pieces ranging in size from tiny grains smaller than sand to chunks as large as houses or even small mountains. Each particle orbits Saturn independently, following its own path governed by gravity and the subtle influences of Saturn's moons. The rings reflect sunlight brilliantly, making them appear bright white or slightly golden depending on the angle of illumination. From Earth, even a small telescope reveals the rings clearly, a sight that never loses its power to amaze. The rings are not uniform. They are divided into distinct bands separated by gaps, each band labeled with a letter in the order of discovery rather than position. The most prominent divisions are the A ring, the outermost major ring visible from Earth, the bright B ring in the middle, and the fainter C ring closest to the planet. Between the A and B rings lies the Cassini division, a gap about 4,800 kilometers wide, named after the astronomer Giovanni Cassini, who discovered it in 1675. Within the Cassini division, material is scarce because particles there orbit at distances where gravitational resonances with Saturn's moon Mimas make orbits unstable, ejecting particles over time and keeping the gap clear. Closer inspection reveals that even the seemingly uniform rings are actually composed of thousands of narrow ringlets, like grooves on a record, each one a slightly different shade or density. Waves ripple through the rings, spiral density patterns created by gravitational interactions with nearby moons. Some regions show propeller-shaped features, where small moonlets embedded in the rings create wakes as they orbit. The rings are dynamic, constantly reshaping themselves on timescales from seconds to millennia, a living structure maintained by the gravitational dance between Saturn, its moons, and billions of orbiting particles. The age of Saturn's rings remains a mystery and a subject of debate. Some scientists believe the rings are ancient, as old as Saturn itself, formed 4.5 billion years ago from material that never coalesced into a moon, or from a moon that was torn apart by tidal forces when it ventured too close to the planet. Others argue the rings are young, perhaps only 100 million years old, formed when a comet or asteroid was shattered by a collision near Saturn, its icy fragments spreading into the magnificent system we see today. Evidence from the Cassini mission, which studied Saturn for 13 years before its planned destruction in 2017, suggests the rings may indeed be relatively young, based on measurements of how quickly they are being contaminated by micrometeorite impacts. If the rings are young, they are a temporary feature, a brief moment of beauty in Saturn's long history, and we are fortunate to live in an era when they exist. Saturn's ring system extends into faint outer structures that are nearly invisible. The tenuous E ring, for instance, stretches from about 180,000 to more than 480,000 kilometers from Saturn's center, reaching beyond the orbit of several moons. This ring is fed by geysers of water vapor erupting from the south pole of the moon Enceladus, ice crystals sprayed into space that spread out to form a gossamer band around the planet. Even farther out, the enormous Phoebe ring, discovered only in 2009 through infrared observations, extends from about 6 million to 18 million kilometers from Saturn, encompassing the orbit of the moon Phoebe and tilted relative to the main rings. These outer structures are so diffuse that they cannot be seen visually, detectable only because their particles absorb and scatter light in specific wavelengths. Saturn hosts a rich family of moons, at least 146 known satellites, more than any other planet. Most are small, irregular chunks of ice and rock, captured asteroids or fragments from ancient collisions. But several are large and geologically interesting, worlds that would merit exploration in their own right, even without Saturn's grandeur to accompany them. Titan, Saturn's largest moon, is unique in the solar system. It is the only moon with a thick atmosphere, a nitrogen-rich blanket denser than Earth's, creating a surface pressure about 50% greater than what we experience at sea level. Titan's atmosphere is opaque, obscuring the surface beneath thick orange haze created by sunlight, interacting with methane and nitrogen, forming complex organic molecules called tholins that give the haze its color. For centuries, Titan remained a mystery, its surface hidden, its true nature unknown. Then in 2005, the European Huygens probe descended through Titan's atmosphere, the first and so far only landing on a moon in the outer solar system. As it fell, it photographed a landscape that looked hauntingly familiar yet utterly alien. Bright highlands and dark plains, drainage channels carved into the terrain, rounded cobbles on the surface. All the features of a world shaped by liquid, yet the liquid is not water. On Titan, it is so cold, about minus 180 degrees Celsius, that water ice is as hard as granite, and methane and ethane exist as liquids. Rain falls from Titan's clouds, not water, but methane, filling rivers that flow into lakes and seas of liquid hydrocarbons. Radar mapping from the Cassini orbiter revealed vast lakes near the poles, some larger than North America's Great Lakes, filled with methane and ethane, shorelines that shift with evaporation and precipitation. Titan is a world with a hydrological cycle like Earth's, but based on entirely different chemistry. Methane evaporates from lakes, rises into the atmosphere, condenses into clouds, and falls as rain, only to flow back into lakes and repeat the cycle. Seasonal changes occur as Titan orbits Saturn, altering which hemisphere receives more sunlight and shifting where rain falls. Beneath the surface, some scientists believe there may be a layer of liquid water mixed with ammonia, a subsurface ocean like those suspected on Europa and Ganymede, making Titan potentially habitable despite its frigid exterior. Enceladus, a small moon only 500 kilometers in diameter, hides its own astonishing secret. Its surface is bright white, covered in fresh ice that reflects sunlight with almost perfect efficiency, making Enceladus one of the most reflective bodies in the solar system. The southern hemisphere is marked by 4 parallel fractures called tiger stripes, and from these fractures erupt geysers of water vapor, ice particles, and organic molecules, plumes that fountain hundreds of kilometers into space. Cassini flew through these plumes multiple times, analyzing their composition, discovering salts and silicate particles that could only come from liquid water in contact with rock. Beneath Enceladus's icy shell, perhaps 30 to 40 kilometers down, lies a global ocean of liquid water, kept warm by tidal heating from Saturn's gravity. This ocean is in contact with a rocky core, creating conditions where hydrothermal vents might exist on the ocean floor, similar to those on Earth that support ecosystems independent of sunlight. The discovery of molecular hydrogen in Enceladus's plumes suggests chemical reactions occurring between water and rock, reactions that on Earth provide energy for microbial life. Enceladus has become, alongside Europa, one of the most promising places in the solar system to search for extraterrestrial life. A small moon transformed by exploration from an insignificant dot of light into a world of profound possibilities. Saturn's other moons include Iapetus, which has one hemisphere as bright as snow and the other as dark as asphalt, a stark contrast whose origin remains debated. Mimas, a small moon with a giant impact crater that makes it resemble the Death Star from science fiction. Hyperion, an irregularly shaped moon that tumbles chaotically through space, its rotation unpredictable. Each moon tells part of Saturn's story, each one shaped by unique circumstances of orbit, composition, and history. The Cassini mission, which orbited Saturn from 2004 to 2017, transformed our understanding of this system. Over 13 years, it executed hundreds of orbits, photographed the rings in unprecedented detail, discovered new moons, measured the compositions of Titan's lakes and Enceladus's geysers, watched storms evolve, and mapped gravitational and magnetic fields. In its final act, controllers commanded Cassini to dive into Saturn's atmosphere, ensuring it would not contaminate potentially habitable moons with terrestrial microbes and gathering data until the very last moment, as atmospheric friction destroyed it. The mission ended, but the data it returned will occupy scientists for decades, each image and measurement revealing new details about this magnificent world. Standing on one of Saturn's inner moons and looking up, if such a thing were possible, you would see the rings arcing overhead like a bridge across the sky, their inner edge disappearing into the planet's shadow. their outer regions glowing brilliantly in sunlight. The rings would move visibly across the stars as you orbited Saturn, their perspective shifting with your position. Saturn itself would loom enormous, a pale golden sphere marked by subtle bands, its hexagonal north pole visible if you were positioned correctly. The view would be one of surreal beauty, a landscape of ice and rock, illuminated by a sun that appears only 1/100th as bright as it does from Earth, yet still sufficient to make the rings shine like a celestial pathway. Beyond Saturn's golden glow, we venture into the cold, dim reaches where sunlight fades to a pale whisper and the planets grow strange in ways that challenge our understanding. Here, nearly 2.9 billion kilometers from the Sun, orbits Uranus, a world so unusual that even its name breaks the pattern. The only planet named for a Greek deity rather than a Roman one. Uranus, god of the sky, grandfather of the Olympians, lends his name to a planet that rolls through space on its side like a cosmic bowling ball, its axis tilted so severely that it essentially orbits the Sun while lying down, its poles pointing where most planets' equators would be. Uranus was the first planet discovered in modern times, found not by ancient observers tracking wandering stars, but by systematic telescopic observation. On March 13, 1781, William Herschel, a German-born British astronomer and composer, was conducting a survey of the sky from his garden in Bath, England, when he noticed what he initially thought was a comet. Further observations revealed that the object moved too slowly and followed too circular a path to be a comet. It was a planet, the first new planet discovered since prehistoric times, instantly doubling the known size of the solar system. Herschel wanted to name it Georgium Sidus, George's star, after King George III. Others proposed Herschel. But eventually, following the tradition of mythological names, astronomers settled on Uranus, continuing the family lineage from Saturn, Jupiter's father, to Uranus, Saturn's father in turn. The most striking feature of Uranus is its extreme axial tilt, approximately 98 degrees. While Earth tilts at a comfortable 23.5 degrees, creating our familiar seasons, Uranus is tilted so far that its rotational axis lies nearly in the plane of its orbit. This means that at various points in its 84-year journey around the Sun, one pole points almost directly at the Sun, while the other remains in darkness. For 42 years, the Northern Hemisphere basks in continuous sunlight, experiencing an endless summer, while the Southern Hemisphere endures an equally endless winter night. Then the seasons reverse. Each pole experiences decades of sunlight followed by decades of darkness, a cycle of extremes unlike anywhere else in the solar system. What caused this extraordinary tilt remains one of planetary science's enduring mysteries. The most widely accepted explanation involves a collision early in Uranus's history, perhaps with another planet-sized body, or a series of impacts from smaller objects. Such a collision would have knocked Uranus onto its side, leaving it tilted ever since. Computer simulations show that a single large impact could achieve this tilt, though other scenarios involving multiple collisions or gravitational interactions during the solar system's chaotic youth might also explain it. The evidence is lost to time, erased by billions of years of subsequent evolution, leaving only the tilt itself as testimony to ancient violence. Uranus is classified as an ice giant rather than a gas giant, though the distinction is subtle and the terminology somewhat misleading. Like Jupiter and Saturn, Uranus has no solid surface and is composed primarily of hydrogen and helium. But these lighter elements make up only about 20% of Uranus's mass. The bulk of the planet consists of heavier materials compressed into exotic states deep within. Beneath the hydrogen and helium atmosphere lies a vast mantle of water, methane, and ammonia ices. Though at the temperatures and pressures that exist there, these substances are not actually frozen solid. Instead, they form a hot, dense fluid, an ionic ocean where molecules break apart under pressure, creating a strange conducting soup where water exists as superheated ice or superionic water, a state where oxygen atoms form a solid lattice while hydrogen atoms flow freely like a liquid. Even deeper, at the planet's core, there may be a rocky kernel composed of silicates and metals, perhaps the original seed around which Uranus accreted during its formation. This core would be about 55% of the planet's radius, compressed to immense densities by the weight of everything above it. The exact structure of Uranus's interior remains uncertain because we have so little data. Unlike Jupiter and Saturn, whose internal heat creates complex weather systems and intense magnetic fields, Uranus is oddly quiet, emitting very little heat beyond what it receives from the distant sun. The atmosphere of Uranus appears remarkably bland, at least when viewed in visible light. The planet glows with a pale blue-green color, serene and featureless, lacking the dramatic bands and storms that mark Jupiter and Saturn. This color comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green. Beneath this deceptively calm exterior, winds blow at speeds exceeding 900 kilometers per hour, and occasional storms erupt. Though they are subtle compared to the Great Red Spot or Saturn's hexagon. When Voyager 2 flew past Uranus in 1986, the images it returned showed a nearly blank sphere, so uniform in appearance that scientists struggled to measure the planet's rotation rate by tracking surface features because there were almost none visible. More recent observations using advanced telescopes like Hubble and ground-based adaptive optics systems have revealed that Uranus is not quite as featureless as it first appeared. Storms do occur, bright clouds that appear and fade, particularly near the poles, as they transition from decades of darkness into sunlight. As Uranus approached its equinox in 2007, when the sun shone directly on the equator, and both hemispheres experienced day and night, atmospheric activity increased, with more clouds and storms visible than at any time since Voyager's visit. These observations suggest that Uranus's atmosphere responds to seasonal changes. Though the mechanisms remain poorly understood, Uranus possesses a magnetic field, but like the planet itself, the field is unusual. It is tilted about 59 degrees relative to the rotation axis and offset from the planet's center by about a third of the radius, as if the dynamo generating it is not located in the core, but in the mantle. This creates a magnetic field that wobbles dramatically as the planet rotates, creating a magnetosphere unlike any other, one that is constantly reconfiguring itself. Solar wind particles, deflected by Jupiter and Saturn's more orderly magnetic fields, interact chaotically with Uranus's off-center, tilted field, creating complex patterns of plasma and radiation. The ring system of Uranus went undetected until 1977, when astronomers observing a stellar occultation, an event where Uranus passed in front of a distant star, noticed that the star's light dimmed several times before and after the planet blocked it. These dimmings revealed the presence of narrow, dark rings encircling Uranus, though far less prominent than Saturn's brilliant bands. Subsequent observations and Voyager 2's flyby revealed 13 known rings, most of them narrow and composed of dark particles, possibly organic compounds created by radiation processing of methane ice. The rings are faint, reflecting only a few percent of the light that hits them, making them difficult to observe from Earth even with powerful telescopes. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, rather than figures from classical mythology, a unique tradition that reflects the planet's status as the first modern discovery. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were all known before Voyager 2's flyby, but the spacecraft revealed their surfaces in detail for the first time and discovered 10 additional smaller satellites. Miranda, the smallest of the 5 major moons, displays one of the most bizarre surfaces in the solar system. Its landscape is a patchwork of wildly different terrain types, as if someone had assembled the moon from mismatched pieces. Smooth plains sit adjacent to regions of chaotic, jumbled terrain. Enormous, chevron-shaped features, called coronae, dominate one hemisphere. Cliff faces rise up to 20 kilometers high, taller than any cliff on Earth. One explanation is that Miranda was shattered by an impact and then reassembled under its own gravity, the pieces not quite fitting together properly. Another suggests that tidal heating from past orbital resonances with other moons caused partial melting and resurfacing, creating the bizarre patchwork we see today. The truth may involve elements of both scenarios, or something entirely different that we have yet to imagine. The other major moons show evidence of past geological activity as well. Ariel's surface is marked by extensive valleys and scarps, signs of tectonic processes that fractured the crust. Umbriel is dark and heavily cratered, ancient and apparently inactive for billions of years. Titania, the largest of Uranus's moons, shows enormous canyon systems that suggest the moon's interior once expanded, cracking the surface as it froze. Oberon, like Umbriel, is heavily cratered, but several of its craters have dark material on their floors, possibly carbon-rich compounds or water mixed with dark organics that welled up from below. Voyager 2 remains the only spacecraft to have visited Uranus. It flew past on January 24, 1986, passing within 81,500 kilometers of the cloud tops. A brief encounter that lasted only a few hours, but transformed our understanding. Every close-up image of Uranus, every detailed measurement of its magnetic field, rings, and moons comes from that single flyby nearly 4 decades ago. Since then, Uranus has been observed only by distant telescopes, watching from afar as the planet continues its slow orbital dance. Its strange tilted rotation, carrying first one pole and then the other into the pale sunlight. The distance and coldness of Uranus pose challenges for exploration. At 2.9 billion kilometers from the Sun, sunlight is about 400 times fainter than on Earth, making solar panels inefficient, and requiring any future mission to rely on nuclear power sources. The journey takes years, nearly a decade, even with gravity assists from other planets. The science return would be immense, answering questions about how ice giants form, why Uranus emits so little heat, what drives its strange magnetic field, and whether its moons might harbor subsurface oceans like those suspected around Jupiter and Saturn. Several mission concepts have been proposed, orbiters that would spend years studying the Uranian system in detail, but none have yet been funded or launched. For now, Uranus remains enigmatic, a world that revealed some of its secrets during one brief encounter and has kept the rest hidden ever since. Farther still, from the sun's warmth, we reach the last of the classical planets, the outermost giant world that marks the edge of where planets larger than Earth can be found. Neptune, the distant blue, a world discovered not by chance or systematic survey, but through the pure power of mathematics, through calculations that predicted where a hidden planet must lie based on the subtle perturbations it caused in Uranus's orbit. When astronomers pointed their telescopes at the predicted location on September 23, 1846, there it was, a faint blue dot exactly where mathematics said it should be, a triumph of human reasoning that revealed a world invisible to the naked eye, lurking in the darkness 4.5 billion kilometers from the sun. Neptune appears as a brilliant blue sphere, deeper and more vivid than Uranus's pale blue-green, a color so striking that it seems almost unnatural, as though someone painted the planet for dramatic effect. Like Uranus, the color comes primarily from methane in the atmosphere absorbing red light and reflecting blue. But Neptune's blue is richer, more saturated. Scientists suspect that an additional unknown compound contributes to the color, perhaps a complex organic molecule or some exotic form of methane created by the planet's atmospheric chemistry, though the exact cause remains a mystery. Whatever creates that intense hue, it makes Neptune one of the most visually stunning planets in the solar system, a jewel of deep cobalt floating in the blackness. Neptune is an ice giant like Uranus, similar in size and composition, yet dramatically different in behavior. Where Uranus appears calm and featureless, Neptune seethes with activity. The planet is racked by the most violent winds in the solar system, storms that race around the planet at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth. These supersonic winds blow in the opposite direction of Neptune's rotation, a retrograde motion that remains poorly understood. How Neptune generates such powerful winds while receiving 900 times less sunlight than Earth, while radiating only a small amount of internal heat, poses a puzzle that challenges our models of planetary atmospheres. When Voyager 2 arrived at Neptune in August 1989, completing its grand tour of the outer planets, it revealed a world far more dynamic than anyone expected. Prominent among the features it observed was the Great Dark Spot, a massive anticyclonic storm similar in relative size to Jupiter's Great Red Spot, spinning in Neptune's southern hemisphere. The storm was enormous, roughly the size of Earth, with winds at its edges reaching 2,400 kilometers per hour, the fastest ever recorded on any planet. White clouds of frozen methane hovered above the dark spot, like cirrus clouds on Earth, indicating that the storm extended deep into the atmosphere, where rising gas brought methane to higher, colder altitudes where it condensed into ice crystals. But Neptune's storms proved far less stable than Jupiter's. When the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had vanished completely, disappeared as though it had never existed. In its place, a new dark spot appeared in the northern hemisphere, demonstrating that these storms are transient features born from the turbulent depths and dissipating after months or years. Subsequent observations have revealed additional storms appearing and fading, white clouds that persist for weeks before dissolving, a dynamic atmosphere that constantly reshapes itself in ways we are only beginning to understand. Like the other giant planets, Neptune has no solid surface. Its atmosphere of hydrogen, helium, and methane gradually transitions into a vast mantle of water, methane, and ammonia. Ices compressed into strange states by immense pressure. Deep within this mantle, conditions may be so extreme that methane breaks down and its carbon atoms compress into diamond. Some models suggest that it rains diamonds on Neptune, crystallized carbon falling through the depths until it reaches layers so hot that even diamond liquefies, forming oceans of liquid carbon thousands of kilometers below the visible clouds. This remains theoretical, impossible to verify directly. Yet the physics suggests such exotic conditions are not just possible, but likely. At Neptune's core, compressed beneath this mantle of exotic ices and possible diamond rain, lies a rocky heart, perhaps a collection of silicates and metals similar to Earth, but compressed to incredible densities. This core might account for as much as 1.2 Earth masses, the original seed around which Neptune accumulated its envelope of lighter materials during the solar system's formation. Unlike Uranus, Neptune radiates about 2.6 times more energy than it receives from the Sun, heat generated either by leftover warmth from its formation or by ongoing gravitational contraction as the planet slowly compresses under its own weight. This internal heat source may explain why Neptune is so much more active than Uranus despite being farther from the Sun and receiving even less solar energy. Neptune's magnetic field, like Uranus's, is severely tilted and offset from the planet's center, inclined about 47 degrees to the rotation axis and displaced by more than half the planet's radius. This creates a complex, asymmetric magnetosphere that wobbles dramatically as Neptune rotates every 16 hours. The magnetic field lines extend far into space on one side and dip close to the planet on the other, creating regions where solar wind particles can penetrate deep into the atmosphere, possibly contributing to the auroras that Voyager 2 detected. Faint glows of excited gases near the magnetic poles. Neptune has a faint ring system, discovered through stellar occultations in the 1980s and confirmed by Voyager 2's images. The rings are dark and narrow, composed of particles that may contain organic compounds darkened by radiation, similar to Uranus's rings, but even fainter. Some sections of the rings appear clumped into brighter arcs rather than being evenly distributed, a feature explained by gravitational interactions with small shepherd moons that corral the ring particles into concentrated regions. These rings are fragile, perhaps temporary on cosmic timescales, slowly eroding as micrometeorites grind the particles down to dust that eventually falls into Neptune's atmosphere, or is swept away by magnetic forces. Neptune's family of moons numbers at least 16, most of them small irregular bodies likely captured from the Kuiper Belt. But one moon dominates, both in size and in scientific interest. Triton, discovered just 17 days after Neptune itself, is the seventh largest moon in the solar system and one of the coldest objects we have ever measured. With surface temperatures around minus 235 degrees Celsius, only 38 degrees above absolute zero, Triton is colder than Pluto, colder than any other moon, a world frozen so solid that nitrogen and methane form ices that behave on Triton like water ice behaves on Earth. Triton is unique among large moons because it orbits Neptune in a retrograde direction, moving opposite to the planet's rotation. This retrograde orbit is powerful evidence that Triton did not form alongside Neptune, but was captured, likely from the Kuiper Belt, where it originated as a dwarf planet similar to Pluto. The capture process would have been violent, requiring Triton to collide with another object or lose energy through gravitational interactions, slowing it enough to be caught by Neptune's gravity. Once captured, tidal forces from Neptune would have heated Triton's interior, possibly melting it entirely and erasing any features from its earlier history. The moon we see today has been reshaped by its capture and subsequent tidal evolution. Voyager 2's flyby of Triton in 1989 revealed a surface unlike any other, marked by cantaloupe terrain, a strange landscape of pits and dimples that covers much of the moon, and by relatively few impact craters, indicating geological activity has resurfaced the moon within the past few 100 million years. The southern hemisphere, which was experiencing summer during Voyager's visit, showed a bright polar cap of frozen nitrogen and methane. Astonishingly, Voyager observed active geysers erupting from this polar cap, dark plumes of nitrogen gas and dust shooting 8 kilometers high before being caught by thin winds and stretched out across the surface for more than 100 kilometers. These geysers, called cryovolcanism, demonstrated that even in the extreme cold of the outer solar system, geological activity can persist, driven perhaps by seasonal heating, as sunlight warms the translucent ice, creating enough pressure beneath to trigger eruptions. Triton's retrograde orbit is slowly spiraling inward. Tidal interactions between Triton and Neptune are gradually stealing energy from the moon's orbit, causing it to move closer to the planet at a rate of about 2 centimeters per year. This process is irreversible. In perhaps 3.6 billion years, Triton will cross Neptune's Roche limit, the distance within which tidal forces will overcome the moon's own gravity and tear it apart. When that happens, Triton will disintegrate into fragments that will spread into a magnificent ring system around Neptune, a ring more extensive and dramatic than Saturn's, though that spectacle lies billions of years in the future, long after the Sun has exhausted its hydrogen fuel and begun transforming into something else entirely. Neptune's other moons are smaller and less remarkable, though each has its story. Nereid, discovered in 1949, follows one of the most eccentric orbits of any moon, swinging from about 1.4 million kilometers from Neptune at its closest to more than 9.6 million kilometers at its farthest, suggesting it too may be a captured object. Proteus, discovered in Voyager 2's images, is one of the darkest objects in the solar system, reflecting only 6% of the light that hits it. and is nearly large enough to have pulled itself into a spherical shape, but remains irregular and lumpy. The smaller moons, most discovered by Hubble and ground-based telescopes years after Voyager's flyby, are likely fragments from collisions or captured Kuiper Belt objects, each one adding a small piece to the puzzle of how Neptune's system formed and evolved. The loneliness of Neptune is difficult to convey. At its distance from the Sun, our star appears only as a bright point of light, still brighter than any star, but no longer a disk, no longer the warm orb that dominates the sky of the inner planets. Sunlight at Neptune is 900 times dimmer than on Earth, reducing high noon to something like deep twilight. Solar panels would generate almost no power. Shadows are sharp and dark. The temperature hovers around -200 degrees Celsius, cold enough that nitrogen would condense into liquid, that oxygen would be a frozen solid. To exist in such cold would require technology beyond anything we possess for long-term survival. Heat sources that could ward off the eternal chill. Insulation against a cold that would freeze human flesh solid in seconds. Yet despite this inhospitable nature, Neptune captivates precisely because it is so active, so dynamic, so alive with storms and winds that seem impossible given the scarce energy available. The planet defies easy explanation, challenging scientists to understand how such violent weather can exist so far from the sun's warmth. Each observation reveals new puzzles. Why do storms appear and vanish? How do supersonic winds persist? What unknown chemistry creates that vivid blue? The answers require more data, more missions, more time spent studying this distant world. Like Uranus, Neptune has been visited only once, by Voyager 2's brief flyby in 1989. Every detailed image, every close measurement, comes from those few days when a spacecraft launched from Earth more than a decade earlier finally reached the solar system's edge and revealed Neptune and Triton in all their unexpected glory. Since then, Neptune has been observed only from afar, a remote blue sphere watched by telescopes straining to discern details across billions of kilometers of space. Mission concepts for returning to Neptune have been proposed, orbiters that would study the planet and its moons for years, perhaps even a probe to Triton to investigate those mysterious geysers and search for evidence of subsurface liquid water. But such missions remain dreams, decades away at best, awaiting the funding necessary to explore the solar system's farthest reaches. Beyond Neptune lies a vast, cold frontier, a region where the architecture of the solar system changes once more. Here, the realm of giant planets gives way to something older, something more primordial. This is the Kuiper Belt, a scattered collection of icy bodies that extends from Neptune's orbit at roughly 30 astronomical units from the Sun outward to perhaps 50 astronomical units or more, a span of billions of kilometers where frozen worlds drift in near darkness, remnants from the solar system's formation that never coalesced into planets, never grew large enough to dominate their surroundings. They remain as they were billions of years ago, time capsules preserving the chemistry and conditions of the ancient solar nebula, waiting in the cold to share their secrets. The Kuiper Belt is named for Gerard Kuiper, one of several astronomers who predicted its existence decades before the first object was discovered there in 1992. The reasoning was elegant. We observe short-period comets, icy bodies that orbit the Sun in periods of a few years to a few decades, and their orbits lie roughly in the same plane as the planets. These comets must come from somewhere, a reservoir of icy bodies beyond Neptune that occasionally get perturbed into the inner solar system. The discovery of the first Kuiper Belt object beyond Pluto confirmed what theory had predicted, and since then, thousands more have been cataloged, with estimates suggesting hundreds of thousands of objects larger than 100 kilometers across populate this distant region. The Kuiper Belt is not a belt in the sense of a concentrated ring. It is more diffuse, more scattered, objects separated by vast distances that make the asteroid belt seem crowded by comparison. Most Kuiper Belt objects, often called KBOs or trans-Neptunian objects, are composed primarily of frozen water, methane, and ammonia, mixed with rock and complex organic compounds. They are dark, reflecting little sunlight, often appearing reddish or brownish due to organic molecules called tholins that form when methane and nitrogen are exposed to cosmic radiation over millions of years. These worlds are cold beyond imagination, with surface temperatures hovering around minus 220 degrees Celsius. So cold that even chemical reactions proceed at glacially slow rates. That ice is harder than granite. That time itself seems to pause. Among the thousands of Kuiper Belt objects, a few stand out for their size and for the questions they raise about how we classify worlds. These are the dwarf planets, bodies large enough that their own gravity has pulled them into roughly spherical shapes, but not massive enough to have cleared their orbital neighborhoods of other debris. The criterion that separates planets from non-planets in the current definition adopted by the International Astronomical Union in 2006. This definition remains controversial, debated by scientists and laypeople alike, but it reflects an attempt to distinguish between the 8 dominant worlds that gravitationally organize the solar system and the numerous smaller bodies that orbit among them. Pluto is the most famous dwarf planet, the former 9th planet, whose reclassification sparked debates that continue to this day. Discovered in 1930 by Clyde Tombaugh after a systematic search for a planet beyond Neptune, Pluto held planetary status for 76 years, featured in textbooks and planetary models as the smallest and most distant member of the solar family. Then, as more powerful telescopes revealed other objects in the Kuiper Belt comparable to Pluto in size, astronomers faced a choice. Either expand the definition of planet to include dozens or hundreds of new worlds, or reclassify Pluto to reflect its nature as one of many large Kuiper Belt objects. The decision to reclassify was scientifically sound but emotionally fraught, particularly for those who grew up learning 9 planets and felt an attachment to Pluto's planetary status. Yet regardless of classification, Pluto remains endlessly fascinating, a world that revealed its true nature only when NASA's New Horizons spacecraft flew past on July 14, 2015, after a journey of 9.5 years across the solar system. The images returned by New Horizons astonished everyone. Where scientists expected a dead, cratered world, They found geological complexity that suggested recent activity, perhaps ongoing even now. Pluto's surface displays a stunning variety of terrain. The western lobe of its most prominent feature, informally named Tombaugh Regio, appears as a vast heart-shaped plain of frozen nitrogen, carbon monoxide, and methane, smooth and crater-free, indicating it formed within the past 100 million years and perhaps much more recently. This plain, called Sputnik Planitia, is a glacier of nitrogen ice that flows slowly, convecting in cells like a lava lamp. As warmer ice rises from below and cooler ice sinks, continuously resurfacing itself and erasing impact craters that would otherwise accumulate. Mountains of water ice, rigid as rock at Pluto's temperatures, rise several kilometers along the plain's edges, their peaks jutting into the thin atmosphere. Elsewhere, Pluto's surface shows ancient, heavily cratered terrain, dark, reddish-brown regions coated in tholins, vast networks of canyons and fractures, and strange, blade-like ridges of methane ice standing hundreds of meters tall, sculpted by sublimation as the ice evaporates directly into gas without melting. Pluto has an atmosphere, thin and tenuous but present, composed primarily of nitrogen, with traces of methane and carbon monoxide. This atmosphere extends more than 1,600 kilometers above the surface, layered with hazes created when sunlight breaks apart methane molecules and the fragments recombine into complex organic compounds. As Pluto follows its eccentric orbit, moving closer to the Sun and then farther away over its 248-year period, the atmosphere freezes and falls to the surface as snow during the coldest parts of the orbit, then sublimes back into gas as sunlight returns. This atmospheric cycle drives weather and climate on Pluto, transporting ice across the surface, depositing it in some regions and removing it from others, creating patterns that change over decades and centuries. Pluto is accompanied by 5 known moons, the largest of which is Charon, a world half Pluto's diameter. Charon is so large relative to Pluto that the two orbit a common center of gravity located in space between them, making Pluto-Charon more accurately described as a binary system than a planet and moon. Charon's surface is primarily water ice, grayer and less colorful than Pluto, marked by canyons and smooth plains that suggest it too experienced geological activity in the past. Charon's northern polar region is stained dark red, a mysterious deposit that may consist of tholins produced from methane escaping Pluto's atmosphere and being captured by Charon's weak gravity, then processed by radiation into the dark compounds we see. The other moons, Styx, Nix, Kerberos, and Hydra, are small and irregularly shaped, likely fragments from an ancient collision that may have formed the entire Pluto-Charon system. Their surfaces are bright, almost white, covered in water ice that reflects much of the faint sunlight reaching them. They tumble chaotically as they orbit, their rotation axes precessing unpredictably due to the complex gravitational influences of Pluto and Charon. Beyond Pluto orbit other dwarf planets, most of them less well known but equally intriguing. Eris, discovered in 2005, is slightly smaller than Pluto, but more massive, composed of denser materials. Its discovery prompted the debate that led to Pluto's reclassification. For if Pluto was a planet, then surely Eris should be as well. And how many more might be discovered? Eris orbits at a much greater distance, currently about 96 astronomical units from the Sun, so far that it receives less than 1,000th the sunlight that Earth does. Its surface is covered in methane ice that appears to sublimate during the brief warmer period of its 558-year orbit, and then refreezes into a fresh layer, giving Eris one of the most reflective surfaces of any object in the solar system, a brightness that contrasts with the dark, reddish surfaces of most other distant bodies. Makemake and Haumea are two more dwarf planets, each strange in its own way. Makemake is reddish-brown, covered in methane and ethane ices mixed with tholins, its surface temperature around -243 degrees Celsius. It has one known moon, a small companion discovered in 2016. Haumea is the most peculiar, shaped not like a sphere, but like an elongated ellipsoid, stretched into a shape resembling a football or rugby ball. It rotates once every 4 hours, faster than any other large body in the solar system, and this rapid spin has distorted its shape, flinging material outward at the equator. Haumea also has two small moons and a tenuous ring system, the only known ring around a dwarf planet, likely debris from an ancient collision that shattered part of Haumea's icy mantle. These dwarf planets are joined by countless smaller Kuiper Belt objects, each with its own orbit, its own composition, its own history. Some follow nearly circular paths in the main Kuiper Belt, stable orbits that will persist for billions of years. Others are scattered disk objects, bodies with highly elliptical and inclined orbits, flung into the outer solar system by gravitational interactions with Neptune during the solar system's youth. These scattered objects can reach hundreds of astronomical units from the Sun at their farthest, venturing into a realm of such darkness and cold that the Sun is merely the brightest star, providing no perceptible warmth. Among the intriguing possibilities in this outer darkness is the hypothetical Planet 9, a proposed world 5 to 10 times Earth's mass, orbiting far beyond the Kuiper Belt, perhaps 400 to 800 astronomical units from the Sun. Evidence for Planet 9 comes not from direct observation, but from the orbital clustering of several distant Kuiper Belt objects whose paths seem to be influenced by the gravity of an unseen massive body. Computer simulations show that a planet in such an orbit could explain these patterns, shepherding distant objects into aligned orbits through repeated gravitational interactions over millions of years. Yet despite searches using some of the world's most powerful telescopes, Planet 9 has not been found. It remains a tantalizing hypothesis, a possible ninth planet hiding in the darkness, or perhaps a statistical anomaly, a pattern in the data that does not reflect an actual object. Time and further observations will tell. The Kuiper Belt is also the source of short-period comets, the icy wanderers that occasionally visit the inner solar system with their glowing tails. Gravitational perturbations from Neptune or close encounters with other Kuiper Belt objects can nudge a body into a new orbit that carries it inward toward the Sun. As it approaches, solar heat begins to vaporize the ices, creating the coma and tail that make comets so spectacular. Each comet is a visitor from the frozen frontier, carrying pristine materials from the outer solar system, offering scientists a chance to study the chemistry of the ancient solar nebula. Missions like ESA's Rosetta, which orbited Comet 67P Churyumov-Gerasimenko, have revealed that comets are complex mixtures of ice, dust, and organic molecules. Rubble piles loosely held together, their surfaces dark and craggy, erupting in jets of gas and dust as sunlight warms their interiors. Speaking of comets, these wanderers carry with them the oldest materials in our solar system, frozen archives from the time before planets, before the sun ignited its nuclear furnace and began flooding the void with light. Comets have inspired awe and fear throughout human history. Their sudden appearances in the night sky, interpreted as omens, as messengers from gods, as harbingers of change. Ancient peoples watched these visitors with wonder and trepidation, not understanding what they were, only that they moved differently from stars and planets, trailing luminous veils across the heavens before fading back into invisibility. Today, we know what comets are, yet they remain no less fascinating, no less beautiful. These dirty snowballs that preserve the chemical signature of our solar system's birth. A comet begins its existence as a frozen nucleus, a chunk of ice and rock and dust that can measure anywhere from a few hundred meters to tens of kilometers across. These nuclei are dark, often black as coal, their surfaces covered in organic compounds and dust that have been altered by billions of years of exposure to cosmic radiation. The ice within is not pure water, but a mixture. Water ice, certainly, but also frozen carbon dioxide, methane, and ammonia, along with more complex molecules, organic compounds that contain carbon, hydrogen, oxygen, and nitrogen, the building blocks from which life is constructed. These icy bodies spend most of their existence in the cold outer reaches of the solar system, dormant and inactive, drifting through the darkness where sunlight is too faint to warm them. But why, when a comet's orbit carries it closer to the sun, something remarkable happens. Solar radiation begins to heat the nucleus, and the ices start to sublimate, transforming directly from solid to gas without passing through a liquid phase. This gas streams away from the nucleus, carrying with it particles of dust that were trapped in the ice. The result is the coma, a vast cloud of gas and dust that surrounds the nucleus and can grow larger than Jupiter, though it contains far less mass. The coma glows faintly, illuminated by sunlight, creating the fuzzy appearance that gives comets their name, derived from the Greek word for hair. As the comet continues its approach, the solar wind, that constant stream of charged particles flowing outward from the sun, pushes on the gas in the coma, sweeping it into a tail that always points away from the sun, regardless of the comet's direction of travel. This is the ion tail, composed of ionized gas, molecules that have lost electrons and now respond to magnetic fields carried by the solar wind. The ion tail glows with a characteristic blue color, light emitted by carbon monoxide molecules as they are energized by ultraviolet radiation. Alongside the ion tail forms a second tail, the dust tail, composed of the particles released from the nucleus. These particles are pushed by the pressure of sunlight itself, photons imparting momentum to dust grains and slowly accelerating them. The dust tail appears yellowish-white. Sunlight reflected from countless tiny particles, and it curves slightly, following the comet's orbital path because the dust particles are heavier and respond more slowly to the sun's influence than the gas does. At its most spectacular, a comet can display both tails stretching for millions of kilometers across space, visible from Earth as a luminous apparition hanging in the twilight sky. The ancient fear they inspired is understandable, for nothing else in the heavens behaves quite this way, appearing suddenly, growing brighter, developing these strange appendages, and then fading as the comet rounds the sun and retreats once more into the darkness. Some comets complete their orbits in just a few years, returning predictably like celestial clockwork. Others take thousands or even millions of years to return, their orbits so elongated that they spend nearly all their time far from the sun, venturing inward only briefly before retreating to the frozen depths. The most famous comet is Halley's Comet, named for Edmund Halley, who in 1705 realized that comet sightings in 1531, 1607, and 1682 described the same object returning every 76 years. He predicted it would return in 1758, and though he did not live to see it, the comet appeared on schedule, confirming his calculations and earning his name for eternity. Halley's Comet has been recorded throughout history, mentioned in Chinese chronicles dating back more than 2,000 years, depicted in the Bayeux Tapestry commemorating the Norman conquest of England in 1066, watched by astronomers and laypeople alike during its most recent appearance in 1986. It will return next in 2061, continuing its ancient circuit. A regular visitor that connects us to every generation that has looked up and wondered at the wandering star with the luminous tail. Comets are divided into two broad categories based on their orbital periods. Short-period comets, those that orbit the Sun in fewer than 200 years, originate primarily from the Kuiper Belt, that region beyond Neptune, where icy bodies drift in relatively stable orbits. Gravitational perturbations from Neptune or close encounters with other Kuiper Belt objects can alter a body's orbit, sending it falling inward toward the Sun, where it begins its transformation into an active comet. These short-period comets often follow orbits that lie close to the plane of the solar system, the same plane in which the planets orbit, reflecting their origin in the flattened disk of the Kuiper Belt. Long-period comets tell a different story. These visitors arrive from all directions, their orbits highly inclined, sometimes even retrograde, and they take centuries, millennia, or even millions of years to complete a single orbit. Their origin lies not in the Kuiper Belt, but in a far more distant and mysterious region called the Oort cloud, a theoretical shell of icy bodies that surrounds the solar system at distances so vast they challenge comprehension. The Oort cloud has never been directly observed. It remains a hypothesis, inferred from the orbits of long-period comets and from our understanding of how the solar system formed. The cloud is thought to begin at about 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units, roughly halfway to the nearest star. To put this in perspective, Pluto orbits at about 40 astronomical units. The Oort cloud lies 50 times farther, extending into a realm where the Sun's gravity is so weak that passing stars can perturb it, where the solar system's boundary begins to blur into interstellar space. The Oort cloud may contain trillions of icy bodies, remnants from the formation of the giant planets that were flung outward by gravitational interactions during the solar system's chaotic youth. As Jupiter, Saturn, Uranus, and Neptune migrated through the early solar system, their gravity scattered smaller bodies in all directions. Some were ejected entirely, lost to interstellar space. Others were flung into the distant reaches where the sun's gravity was just strong enough to hold them in extremely elongated orbits. Over billions of years, these bodies settled into a roughly spherical shell, the Oort cloud, a reservoir of frozen material that preserves the chemistry of the ancient solar nebula. Occasionally, a passing star's gravity or the tidal effects of the Milky Way galaxy itself will perturb the orbit of an Oort cloud object, nudging it slightly, just enough that it begins falling inward toward the sun. This journey can take millions of years, the comet accelerating as it approaches, finally entering the inner solar system, where sunlight warms it and transforms it into the spectacular visitors we observe. Some of these comets, after one pass around the sun, return to the Oort cloud, their orbits barely altered. Others are captured into shorter orbits by gravitational interactions with Jupiter or the other giant planets, becoming short-period comets. And some are accelerated so much that they achieve escape velocity and are ejected from the solar system entirely, becoming interstellar wanderers destined never to return. When comets do not fall all the way to the sun, but instead fragment in Earth's atmosphere, we witness meteors, those fleeting streaks of light that trace across the night sky. Most meteors are not from comets' nuclei, but from the dust they shed, particles no larger than grains of sand that remain in the comet's orbital path long after the comet itself has passed. When Earth's orbit intersects one of these debris streams, the particles slam into our atmosphere at speeds of tens of kilometers per second. The friction heats them to thousands of degrees, vaporizing them in a flash of light that lasts less than a second. These are the shooting stars that people wish upon, brief and beautiful, the dying breath of cosmic dust. Certain times of year produce meteor showers when Earth passes through particularly dense debris streams left by known comets. The Perseids in August, debris from Comet Swift-Tuttle, can produce more than 60 meteors per hour during their peak. The Leonids in November, remnants of Comet Tempel-Tuttle, occasionally produce meteor storms with thousands of meteors per hour, the entire sky filled with streaking lights. The Geminids in December, interestingly, come from an asteroid, 3200 Phaethon, which may be an extinct comet that has shed all its volatile ices and now appears rocky. Each meteor shower has its own character, its own parent body, its own story of orbital mechanics and cosmic coincidence. Occasionally, a meteor is large enough to survive its passage through the atmosphere and reach the ground. These survivors are called meteorites, and they provide scientists with actual samples of extraterrestrial material that can be studied in laboratories. Most meteorites come not from comets, but from asteroids, chunks of rock and metal that are more durable than the fragile, icy nuclei of comets. But some meteorites, particularly those rich in carbon and water, likely originated in the outer asteroid belt or even from comets, bringing to Earth materials that formed in the cold outer regions of the solar nebula. Analysis of these samples has revealed organic molecules, amino acids, and even traces of water, supporting the hypothesis that comets and asteroids delivered the ingredients for life to early Earth during the heavy bombardment period billions of ago. The cosmic cycle continues even now. Comets and asteroids still fall toward the sun, still deliver water and organic molecules to the inner solar system, still impact planets and moons, though far less frequently than in the solar system's violent youth. Each impact, each meteor shower, each comet appearance reminds us that space is not empty, but filled with travelers, with wanderers that connect the present to the ancient past, that carry materials between worlds, that blur the boundaries between planets and the space between them. Standing at the edge of the Oort cloud, if such a thing were conceivable, you would be so far from the sun that it would appear as nothing more than the brightest star, no different to the naked eye from Sirius or Canopus or any other brilliant point in the vast stellar tapestry. The temperature would be only a few degrees above absolute zero, so cold that all molecular motion nearly ceases, that even helium would condense into liquid. The icy bodies of the Oort cloud would be invisible, separated by millions of kilometers, dark and frozen, unaware of the sun that still holds them in its gravitational embrace. Time would move differently here, where an orbit takes not years but eons, where the stars themselves shift position noticeably over the course of a single revolution, where the galaxy turns and seasons last longer than species survive. This is the boundary of the sun's domain, the place where our star's influence fades to a whisper, where the solar system ends and interstellar space begins. Beyond lies the void between stars, distances measured not in astronomical units, but in light years, where comets ejected from our solar system drift through darkness that will never end, where the sun becomes just another star among billions, its family of planets invisible, its story known only to those who lived within its light. Our journey has taken us far, from the blazing heart of the sun to the frozen silence at the solar system's edge. We have traveled billions of kilometers through space and billions of years through time. The scale of what we have explored is difficult to hold in mind. Light from the sun, traveling at 300,000 kilometers per second, takes 8 minutes to reach Earth, but more than 4 hours to reach Neptune. The distances are so vast that our fastest spacecraft take years or decades to traverse them. Yet for all this immensity, our solar system is but a tiny island in the cosmos, one star among hundreds of billions in our galaxy, one planetary system among countless others scattered across the universe. The perspective is humbling, yet somehow comforting. We are small, yes, but we are part of something vast and ancient and beautiful. Everything in our solar system is connected. Jupiter's gravity shaped the asteroid belt and shields Earth from impacts. The moon stabilizes our planet's tilt and creates the tides. Saturn's moon Enceladus sprays water into space, feeding the planet's E-ring. Comets from the Kuiper Belt deliver ice and organic molecules to the inner solar system. Even now, spacecraft are traveling outward, carrying messages and instruments, extending humanity's reach into the darkness. Missions are being planned to return to Venus, to orbit Uranus, to land on Titan, to drill through Europa's ice. The exploration continues, each discovery raising new questions, each answer revealing deeper mysteries. We are made of the same stardust that forms these distant worlds. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in stars that died long before the sun was born. We are not separate from the cosmos, but intimately woven into its fabric, participants in a story that spans the lifetime of the universe itself. So breathe deeply now. Let your thoughts drift like spacecraft through the solar system we have explored together. Let the planets carry you gently toward sleep, each one a waypoint on the journey into dreams. The cosmos is vast, and you are small, but you are here. You are aware, and that itself is a kind of miracle. Good night.